Here is the conclusion before we have earned it. Before the evidence, before the arguments, before the long walk through a year of the strangest astronomy any of us have lived through. The verdict, delivered up front, the way a jury foreman stands up in a quiet courtroom and reads a single word off a folded slip of paper. Nothing came out of it. On the 16th of March, 2026, an object born around a star that no longer exists, older than the sun, older than the Earth, older than almost everything we can point a telescope at, swept past the largest planet in our solar system at a distance so precisely tuned that a Harvard astronomer had calculated the odds of the coincidence at roughly 1 in 25,000. Every serious telescope on Earth was watching. A spacecraft in orbit around Jupiter was watching. A second spacecraft, still years from arrival, had already photographed it from an angle no human eye had ever occupied. And nothing came out of it. No probes, no moon, no maneuver, no signal, no engine burn, no course correction, no beacon, no whisper on any of the billions of radio channels that a team in Northern California swept for more than 7 hours with a 42-dish array. The interstellar object 3I/Atlas passed Jupiter, and it kept going, and it faded, and it is now a dot too faint for most instruments to hold, falling out of our sky toward the constellation Gemini at 58 kilometers per second, and it will never come back. That is the ending. And if you have followed this story at all over the past year, you already know that the ending is not the interesting part. Because the question that dominated the internet, that dominated dinner tables and podcasts and congressional correspondence and, quietly, more than a few conversations inside the astronomical community itself, was never really is it aliens. The question was something stranger and more uncomfortable and much harder to put down. The question was, how would we actually know? What precisely would have to happen at Jupiter for a reasonable person to change their mind? And when the answer to that question was written down in advance, published, time-stamped, made falsifiable, and then tested against reality, when a scientist did the thing science is supposed to do and said, here is my prediction, here is the date, here is what would prove me right, what happened next is a story about how human beings handle being wrong. And about how a small number of people looked at the same data and concluded, not that the hypothesis had failed, but that the object had simply gotten better at hiding. This is the Jupiter anomaly. And to understand why it mattered, why it consumed an entire year of scientific attention, why a member of the United States Congress wrote a letter to NASA about it, you have to go back to a warm night in the Chilean desert and a telescope doing exactly what it was built to do, which was not this. The Asteroid Terrestrial Impact Last Alert System is not a glamorous instrument. It is not the Hubble. It is not the James Webb. Atlas is a network of modest telescopes, half-meter mirrors, roughly the size of a large dinner plate, scattered across Hawaii, Chile, and South Africa, and its entire purpose is to be the smoke alarm of the solar system. It sweeps the whole visible sky every night or two, comparing each new frame to the last, looking for the one point of light that has moved. It is looking for the rock that has our name on it. It is the least romantic job in astronomy and arguably the most important, and it is funded by NASA for exactly that reason. On the 1st of July 2025, the Atlas station in Rio Hurtado, Chile, caught something moving through the constellation Sagittarius in the direction of the galactic center and flagged it the way it flags a few thousand things a year. Within days, the flag turned into something else entirely. Because when astronomers took the handful of positions Atlas had recorded and fit an orbit to them, the fit came back wrong. Not wrong in the sense of a mistake, wrong in the sense that the shape of the path did not close. Every object that belongs to our solar system, every asteroid, every comet, every dwarf planet out past Neptune travels a closed loop, an ellipse. It may take 3 years or 30,000, but it comes back. That is what it means to be gravitationally bound to the sun. The number that describes how stretched that ellipse is called eccentricity, and for a closed orbit it is always less than 1. A circle is 0. Earth's orbit is 0.017, almost a perfect circle. Halley's Comet, on its long dive from beyond Neptune to inside the orbit of Venus, is 0.967, dramatically stretched but still, in the end, a loop. Cross the value of 1 and the geometry changes character entirely. You are no longer on an ellipse. You are on a hyperbola, an open curve, a path that comes in from infinity and goes back out to infinity, bending around the sun once and never returning. The eccentricity that came back for this object was above 6. Not 1.01, the sort of value you get from a comet nudged by Jupiter into a barely open trajectory. 6. It was the most hyperbolic orbit ever measured for anything, and there was no ambiguity about what it meant. The Sun had not made this thing. The Sun had not captured this thing. The Sun was, at most, briefly borrowing it. It was given the designation 3I/Atlas. The 3 because it was the third. The I for interstellar. To understand what a small number that is, consider what came before. In October 2017, a telescope in Hawaii spotted the first one, and the name it received, Oumuamua, a Hawaiian word meaning something like a scout, a messenger reaching out from the distant past, was appropriate in ways nobody appreciated at the time. It was small, a few hundred meters at most, and it was gone almost before anyone could react. We got weeks of data. What that data showed was maddening. Its brightness varied by a factor of 10 as it tumbled, which implied a shape so elongated that a cigar was the polite comparison and a pancake was the more likely reality. It showed no coma, no tail, none of the fuzzy halo of vaporizing ice that defines a comet. And yet it accelerated. Something pushed it away from the Sun with a gentle, sustained force that gravity alone could not account for. And to this day, there is no consensus explanation that satisfies everyone. Frozen hydrogen. Frozen nitrogen sheared off the surface of an exopluto. A fragment of a shredded planet. A solar sail. That last suggestion came from Avi Loeb, then the chair of Harvard's astronomy department, and it earned him a great deal of attention, a best-selling book, and a permanent position in the discourse that he has occupied ever since. 2 years later, an amateur astronomer in Crimea named Gennady Borisov, using a telescope he had built himself, found the second. 2I/Borisov was, by comparison, deeply reassuring. It was a comet. It looked like a comet, it behaved like a comet, it had a coma and a tail, and it outgassed the things comets outgas. It was chemically a little unusual, unusually rich in carbon monoxide, but it fit. It said, "The galaxy makes objects like ours. Fine, good, normal." And then, for 6 years, nothing. Which brings us to the summer of 2025, and an object that was not going to be reassuring at all. The first thing that separated 3I/Atlas from its two predecessors was size. Oumuamua was perhaps 100 meters across. A New York City block. Borisov was under a kilometer. Early estimates of 3I/Atlas, based on how much light it reflected, ran alarmingly large, and while a bright coma makes any comet look bigger than it is, Hubble observations in August 2025 pinned the nucleus somewhere between 440 meters and 5.5 kilometers. Call the upper end 3.5 miles. That is a solid object the size of a mid-sized American city, and if it were the upper end, it would be roughly 1,000,000 times more massive than Oumuamua and 1,000 times more massive than Borisov. And here is the part that made theorists uncomfortable. The galaxy is not supposed to be able to afford that. Interstellar objects are the debris of planet formation, the stuff flung out of young star systems by the gravitational bullying of newborn giant planets. There is a lot of it out there, but it follows a distribution. For every large piece, there are vastly more small ones. We had found 3 objects. Finding the third one and having it be 1,000,000 times more massive than the first is like walking into a casino, playing 3 hands, and having one of them pay out more than the other 2 combined by a factor of 1,000,000. It is not impossible. It is a statement about how much stuff must be out there for that to be a fair draw. Some calculations suggested you would need more rocky material floating between the stars than there are stars to have made it. The second thing was speed. 3I/Atlas came in at roughly 58 kilometers per second relative to the Sun, about 130,000 miles an hour, fast enough to cross the continental United States in under 90 seconds. That is faster than either of the previous 2. And speed, in this context, is a clock. Objects drifting in the galaxy get gravitationally stirred over time by every star and gas cloud they pass, and the longer they drift, the faster and more scattered their motions become. This is a well-understood relationship in galactic dynamics, and read backward, it says something specific. It said this object had been traveling for a very long time. It said its velocity was characteristic of the thick disk of the Milky Way, the older population of stars that sits above and below the thin plane where our Sun lives. It said, in the careful language of a NASA briefing, that it probably predates our solar system. Tom Statler, NASA's lead scientist for small bodies, said out loud in a press conference that the thought gave him goosebumps. That is not a phrase that survives a NASA press office review by accident. And then the observations started coming in, and the list of things that did not fit began to grow. It is worth understanding exactly how that determination gets made, because the speed of it is one of the quiet marvels of modern astronomy, and because the machinery involved is almost entirely invisible to the public. When a survey telescope finds a moving point of light, the observation goes to the Minor Planet Center, an operation housed at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, and sanctioned by the International Astronomical Union. The MPC is the clearinghouse for every small body in the solar system. It receives something like 100 million observations a year from professional surveys, amateur astronomers, and space telescopes, and its job is to sort out which points of light on which nights belong to the same object, and to compute where that object will be next. An object flagged as potentially unusual goes onto a public confirmation page, and here the network activates. Observers around the world, including a remarkable number of amateurs with backyard equipment that would have been world-class research apparatus 40 years ago, point their telescopes at the predicted position and report what they see. Each new observation extends the arc. And the longer the arc, the more tightly constrained the orbit becomes, because fitting a curve through 3 points scattered over 2 nights leaves enormous freedom, and fitting one through 200 points scattered over 3 weeks leaves almost none. For 3I/Atlas, the arc closed fast, and it closed on an answer nobody could argue with. Then came the archival dig, the process astronomers call precovery, in which you take the newly determined orbit, run it backward in time, calculate where the object must have been on previous nights, and go looking through the accumulated image libraries of every survey on Earth for a faint smudge that nobody had reason to notice. That is how the June 21st activity was found. The object had been sitting in the data. It had been photographed before it was discovered. It simply had not been recognized, because a dim dot moving slowly against the stars at nearly 5 astronomical units looks like 1,000 other things until you know what you are looking for. By mid-July, the designation was official. C/2025 N1 as a comet, 3I/Atlas as an interstellar object. Third of its kind in the entire history of the human species. And almost immediately, the other conversation started. This is not a new phenomenon, and it is important to know the pattern, because astronomy has a long and instructive history of anomalies that looked artificial and were not, and the history is not a story of foolishness. It is a story of a discipline learning what its own ignorance looks like. In the 1870s, an Italian astronomer named Giovanni Schiaparelli mapped features on Mars that he called canali, channels, in Italian, a word that does not imply construction. Translated into English as canals, the word acquired an engineer, and the American astronomer Percival Lowell spent 2 decades and a considerable personal fortune building an observatory in Arizona and elaborating a theory of a dying civilization irrigating a desiccating planet from its polar caps. He published maps of the network. He wrote best-selling books. He was wrong. The canals were an artifact of the human visual system attempting to resolve low-contrast detail at the limit of what refracting telescopes of the era could deliver. But Lowell's observatory, built for canals, is where Pluto was found in 1930, and the search for planetary detail he inspired shaped a generation of planetary science. Being wrong productively is a real category. In 1967, a graduate student at Cambridge named Jocelyn Bell, working with a radio telescope she had helped build out of wire and wooden posts across 4 acres of English field, found a signal in her chart recordings that pulsed with a period of 1 1/3 seconds and a regularity that was, at the time, unprecedented in nature. Nothing in the sky was known to keep time like that. The source was labeled, half in jest and half not, LGM-1, Little Green Men 1. Bell and her supervisor Anthony Hewish took the possibility seriously enough to work through it methodically, and what settled the matter was a second source in a completely different part of the sky doing the same thing. 2 independent civilizations transmitting on the same principle at the same time was not a plausible hypothesis. What they had found were pulsars, the collapsed neutron star cores of dead stars, city-sized, spinning up to hundreds of times a second, sweeping beams of radiation across the galaxy like lighthouses. It was one of the great discoveries of 20th century astrophysics, and it began as a suspected alien signal, and the suspicion did no harm at all because it was tested. In 1977, A radio telescope in Ohio recorded a narrowband burst so far above the background that the astronomer reviewing the printout the next day circled it and wrote a single word in the margin. Wow. The wow signal lasted 72 seconds, matched the profile of a genuine celestial source rather than terrestrial interference, and has never been detected again despite decades of attempts. It remains unexplained. Nobody serious claims it was extraterrestrial. Nobody serious can tell you what it was either. Sometimes the honest answer is a permanent question mark, and a mature science has to be able to file things there without either forgetting them or inflating them. And in 2015, an object with a designation that meant nothing to anyone, KIC 8462852, quickly nicknamed Tabby Star after the astronomer Tabitha Bayagian, began producing the strangest light curve in the Kepler dataset. Its brightness dropped irregularly by as much as 22% in patterns that no transiting planet could produce. A planet passing in front of a star blocks a fraction of a percent and does it on a fixed schedule. This was enormous, aperiodic, and shaped wrong. A paper co-authored by Jason Wright raised, in careful language, the possibility of an alien megastructure, a Dyson swarm, a civilization's partially built energy-collecting apparatus, not because anyone believed it, but because it belonged on the list of hypotheses. The press did what the press does. Crowd-funded observing campaigns followed. And the answer, when it came, was dust. Uneven clouds of fine material, revealed by the fact that the dimming was wavelength-dependent, blocking blue light more than red, which solid objects do not do and dust does. Tabby Star is still not fully explained, but it is not engineering. For cases, for anomalies that looked artificial, for natural answers, or in one case an honest and enduring blank. The pattern is not that scientists are gullible. The pattern is that the exotic hypothesis is raised, tested, and discarded, and that the process of discarding it usually produces the real discovery. Pulsars, wavelength-dependent extinction, the limits of visual resolution. That is the return on investment for taking weird things seriously. 3i/Atlas was going to run through that same machine. The difference this time was speed and scale, and the fact that the machine was now running in public, in real time, in front of an audience of hundreds of millions with the capacity to talk back. None of this can be understood without going back 8 years, because 3i/Atlas did not arrive into a neutral conversation. It arrived into an argument that had been running since 2017 and had never been settled, and the shape of that earlier argument determined the shape of this one before a single observation was made. On the 19th of October, 2017, the Pan-STARRS telescope on Haleakala, on the island of Maui, recorded a faint moving object. Robert Warwick, the postdoctoral researcher who spotted it, checked the orbit and could not make it close. Within days, the answer was inescapable. It was the first. It was given a Hawaiian name, Oumuamua, roughly a scout or a messenger arriving first from a great distance, and it became, for a few weeks in the autumn of 2017, the most photographed object in astronomy. The trouble was that it was already leaving. By the time anyone knew what it was, it had already passed perihelion, already made its closest approach to Earth, and was accelerating away. The total observational window was about 2.5 weeks of usable data from a handful of large telescopes, and then it was too faint. That is the entire dataset. Everything anyone has ever argued about Oumuamua rests on 11 days of photometry and a scattering of spectra, and there will never be more. What that thin dataset showed was a sequence of properties that individually strained belief and collectively broke it. Its brightness varied by a factor of about 10 as it tumbled. That variation is a shape measurement. A rotating object presents different cross-sections to the Sun, and a factor of 10 implies an axis ratio of at least 6:1, possibly 10:1. Nothing in our solar system looks like that. Asteroids are lumpy potatoes with axis ratios of maybe 2:1. Gravity rounds things off, and the ones that stay elongated are usually contact binaries, two bodies gently touching. A 10:1 object is a Planck. Later analysis suggested the data were equally consistent with a flattened disk, a pancake rather than a cigar, which was, if anything, stranger. It showed no coma, no tal, no detectable gas of any kind, at any wavelength anyone looked. By every observational criterion, it was a bare rock. And it accelerated. The trajectory fit required an extra outward push, falling off with distance from the sun, sustained and unambiguous, and far too large to be radiation pressure on an ordinary rock. Those last two facts are in direct conflict. Comets accelerate because they vent gas. Oumuamua accelerated and did not vent anything anyone could see. Every explanation proposed since has been an attempt to reconcile that contradiction, and everyone has a problem. Perhaps it vented pure molecular hydrogen, an iceberg of frozen hydrogen, which would sublimate readily and be nearly invisible spectroscopically. The problem is that hydrogen ice requires temperatures within a couple of degrees of absolute zero to form, and it is not clear such a body could survive a journey through the galaxy without evaporating from starlight alone. Perhaps nitrogen ice, a fragment blasted off the surface of an exopluto, since Pluto's surface is largely nitrogen ice. The problem is the mass budget. Producing enough such fragments to make one likely to pass by requires an implausible amount of shattered dwarf planets. Perhaps it was a fluffy fractal aggregate, 100 times less dense than water, so tenuous that ordinary sunlight could push it. The problem is surviving ejection and 10 million years of travel without compacting. And perhaps, as Avi Loeb argued in a paper with Shmuel Bialy, and then in a book that sold very well and made him a household name in a way that no astronomy department chair has ever quite wanted to be, it was a light sail. An artificial structure, thin and broad, pushed by sunlight, which would explain the acceleration without outgassing and the extreme shape as a consequence of function. The reaction was ferocious, and it is important to note what the reaction was actually about, because it was not primarily about whether the hypothesis was true. Very few of Loeb's critics claimed to have a satisfying explanation of their own. The honest position among specialists was and remains that Oumuamua is unexplained. The objection was to the epistemics, to the argument that because the natural explanations were all strained, the artificial one deserved elevated standing. Critics pointed out that this reasoning applied to any sufficiently underobserved phenomenon would produce aliens everywhere, and that a sample of one object seen for 11 days is precisely the regime in which you should expect to be confused by ordinary things. That argument never resolved. Could not resolve because the object was gone and the data were fixed. Simply sat there unfinished for 8 years. And then a second interstellar object arrived, and it was Borisov, and it was a perfectly ordinary comet. And it did nothing to settle anything because a normal object cannot explain an abnormal one. So when the third one appeared in July 2025, the argument was still loaded, still unresolved, with both sides still holding their positions from 2017, and now a target that would be observable not for 11 days but for a full year, with instruments that had not existed the first time. That is why this became what it became. It was not really a new argument. It was a rematch with better equipment. And it is worth noticing what happened to the specific claims across the two cases, because the contrast is instructive. Oumuamua accelerated without visible outgassing, and the artificial hypothesis was invoked to explain the acceleration. 3I/Atlas outgassed enormously and initially showed no measurable acceleration, and the artificial hypothesis was invoked to explain the absence. Then it did accelerate, and the artificial hypothesis was invoked to explain the presence. 3 different observational situations. 3 opposite results. 1 conclusion, available for all of them. That is not a gotcha, and it should not be delivered as one. It is a diagnostic. When a framework can accommodate a phenomenon, its opposite, and its absence, the framework has stopped constraining anything, and the only remaining question is whether the person holding it can notice. 3I/Atlas did something Oumuamua never could. It gave us a year and a specified test and a date. It gave the argument a chance to be settled rather than abandoned. That, more than anything, is what made the 16th of March 2026 matter. Start with the water, because water is where every comet story begins. A comet is, in the old and still basically correct formulation, a dirty snowball. It spends its existence in deep freeze, and when it falls toward a star, the ice does not melt, because there is no atmosphere to hold a liquid. It sublimates. It goes straight from solid to gas, and the escaping gas drags dust with it, and that expanding cloud is the coma, and the pressure of sunlight and the solar wind blow it back into the tail. Water ice, specifically, does not begin doing this in earnest until a comet gets within about 3 astronomical units of the Sun. 3 times the Earth-Sun distance, roughly the middle of the asteroid belt. Farther out than that, water ice is simply too cold to care that a star is nearby. NASA's Swift Observatory detected water coming off 3I/Atlas at 2.9 astronomical units, right at the edge. And the rate was not a trickle. The inferred water loss was around 40 kilograms per second, with something like 8% of the surface actively venting, which is high for a comet that far out and high for a comet of that size at any distance. Recovery images, old frames pulled from archives after the fact, where the object had been sitting unrecognized in data nobody had reason to examine, showed it was already active on the 21st of June, 2025 at 4.85 astronomical units, well beyond the asteroid belt out near Jupiter's orbit. It had a coma 25,000 kilometers across, roughly twice the diameter of Earth, before it had any business having one at all. Then came the chemistry, and the chemistry is where things got genuinely strange. The James Webb Space Telescope turned its instruments on the object and measured the composition of the gas coming off it. And what it found was a coma dominated not by water, but by carbon dioxide. The ratio of carbon dioxide to water was among the highest ever recorded for any comet anywhere. Dry ice, not water ice, was running the show. Ground-based spectroscopy at the Very Large Telescope in Chile found something else. Strong emission lines from neutral nickel vapor and almost no iron. That combination raised eyebrows for a reason that has nothing to do with astronomy. Nickel and iron travel together in nature. They condense together in the cores of dying stars. They are alloyed together in meteorites. They are alloyed together in Earth's core. Finding nickel without iron is, in a terrestrial context, a signature of industry, of refining, of deliberate separation, of the kind of thing that happens in a smelter rather than a nebula. And 3I/Atlas was releasing more nickel than any comet in our solar system, and more than Borisov had. Loeb noticed. Of course he noticed. And here it is worth pausing, because the shape of this entire story depends on understanding the man at the center of it, and the caricature does not serve anyone. Avi Loeb is the Baird Professor of Science at Harvard. He chaired its astronomy department for 9 years. He founded its Black Hole Initiative. He served on the President's Council of Advisors on Science and Technology. He has published hundreds of papers on subjects that have nothing to do with extraterrestrials, and his work on the formation of the first stars is standard reading. He is not a crank, and treating him as one is both unfair and analytically useless. What he is a scientist who made a strategic decision about how to spend his professional capital, and who has argued consistently, publicly, and with a certain relish, that the astronomical community has developed a reflex of dismissing anomalies it cannot explain rather than sitting with them. His line, delivered at a conference where a colleague had just demonstrated that the disagreement over the universe's expansion rate was statistically undeniable, is worth quoting because it is the thesis of his entire enterprise. It is bad professional practice for theorists to conclude the data must be wrong just because they have no explanation for it. That is a defensible position. It is, in fact, close to a truism. The trouble is what happens when you apply it as a general method, which is that you begin to accumulate anomalies, and an accumulating list of anomalies has a psychological gravity of its own that has very little to do with its evidentiary weight. By late 2025, the list had 8 items on it, then 9. By November, it was organized by probability, each entry tagged with the odds Loeb assigned to it occurring by chance. By March 2026, there were 22. Nickel without iron, carbon dioxide dominance, anomalous mass, early activity, extreme speed, and the ones about geometry, which are where the argument turned from chemistry to choreography, and where the Jupiter anomaly was born. Because 3I/Atlas did not arrive on a random trajectory. It arrived on a retrograde orbit, moving opposite to the direction of the planets, inclined by only about 5 degrees to the ecliptic, the flat plane in which every planet in our solar system orbits. Think of the solar system as a phonograph record with the sun at the spindle. Objects falling in from the galaxy have no reason to respect the record. They should come in from any angle at all. From above, from below, at 40 degrees, at 80. Oumuamua came in steeply. The odds of an object arriving within 5 degrees of that plane by chance are, by Loeb's calculation, about 1 in 500. And traveling in that plane, it passed close to things. On the 3rd of October 2025, it swept within 0.19 astronomical units of Mars, 29 million kilometers, close enough that the fleet of orbiters at Mars could be pointed at it, close enough that NASA's Mars Reconnaissance Orbiter, whose high-rise camera is the sharpest eye anyone has ever placed at another planet, was tasked to look. It passed within tens of millions of kilometers of Venus, and it reached perihelion, its closest approach to the Sun, at 1.36 astronomical units, just inside the orbit of Mars, on the 30th of October 2025, at a moment when it was positioned on the far side of the Sun from Earth, hidden, unobservable from the one planet with people on it, during precisely the window when the most dramatic changes would be occurring. Loeb assigned that arrangement odds of 1 in 20,000. And then there was Jupiter. The forecast, computed from the orbit and refined repeatedly as more observations came in, put 3I/Atlas at its closest approach to Jupiter on the 16th of March 2026, at a distance of 53.56 million kilometers, plus or minus about 450,000. In astronomical units, 0.358. Now, that number by itself is unremarkable. 33 million miles is not close by any human standard. It is more than a third of the distance from the Earth to the Sun. Jupiter's own moon Callisto orbits at under 2 million kilometers. This was not a flyby in any dramatic sense. Juno would not be able to photograph a surface. The object would remain a fuzzy dot. But there is a number attached to Jupiter that almost nobody outside of celestial mechanics has ever heard of, and it is 53.5 million kilometers. That number is the Hill radius. It is the boundary of Jupiter's gravitational kingdom. Inside it, Jupiter's pull dominates. Outside it, the Sun's tidal influence takes over and strips away anything trying to orbit. Every one of Jupiter's 95 known moons lives inside that sphere. It is the outer wall of the castle, and it is not a wall you can see or feel. It is a mathematical surface defined by the mass of Jupiter, the mass of the Sun, and the distance between them. It is one of the most abstract objects in orbital mechanics, and the interstellar visitor's closest approach fell within a hair of it. Refine the trajectory further, folding in the small non-gravitational acceleration the object had displayed near perihelion, and the numbers get tighter still. A Perihove distance of 53.445 million kilometers against a Hill radius of 53.502 million. A match to within about 1 part in 1,000. Loeb assigned that coincidence a probability of 0.00004. 1 in 25,000. And then he did the thing that turned a curiosity into a genuine scientific event, which was to state in advance what it would mean and how it could be tested. Here is the logic, and it is worth following carefully, because it is elegant and it is falsifiable, and those two qualities together are rare in this corner of the discourse. If you were an engineer and your objective was to deposit hardware into permanent orbit around Jupiter, and you were arriving on a hyperbolic trajectory at enormous speed, the single most fuel-efficient place to release that hardware would be exactly at the edge of the Hill sphere. Out there, the escape velocity from Jupiter is tiny, about 2.2 kilometers per second. A released object needs only a small nudge to settle into a bound orbit rather than sailing past. The Lagrange points, L1 and L2, sit near that boundary, and they are the parking spots of the solar system. Locations where the gravitational tug of two bodies balances such that station keeping costs almost nothing. If you wanted to leave something at Jupiter and you were only passing through once, forever, at high speed, the Hill radius is where you would do it. The trouble, and Loeb spelled this out himself, is the arithmetic of the velocity. At closest approach, 3I/Atlas was moving at about 66 kilometers per second relative to Jupiter. To leave anything behind in a bound orbit, that relative motion has to be cancelled almost entirely. Something released from the object would need a velocity kick of roughly 66 kilometers per second in precisely the right direction to end up captured rather than continuing on out of the solar system with its parent. And that is where the test lives. Because 66 kilometers per second is not a speed that nature can produce this way. When a comet fragments, and comets fragment all the time, they crack under thermal stress and rotational forces, and they shed pieces constantly. The fragments separate at speeds measured in meters per second. Centimeters per second, often. The gravitational binding energy of a 5-kilometer object simply does not contain the energy to fling debris at 66 kilometers per second. To put that in perspective, the escape velocity from the surface of Jupiter itself, the entire planet, 318 Earths of mass, is 60 kilometers per second. A comet cannot throw a rock harder than Jupiter can throw a rock. The physics forbids it. Therefore, Loeb wrote, if a new moon of Jupiter appeared after the 16th of March 2026, a 96 satellite in a bound orbit that had not been there before, it could not be a natural fragment. It would be a deliberate deposit. It would constitute, in his phrasing, a clear technological signature. "Get your popcorn ready by March 16th, he wrote. There is something admirable in that, and it should be said plainly. He had named a date, named an observable, named a threshold, and named what would count as confirmation. Whatever else you think of the hypothesis, that is the correct structure for a claim. It is more than most of the people arguing about this online ever managed. The question was who would be watching and with what. To appreciate what that number means, you have to appreciate Jupiter, and most people do not, because Jupiter has been in every science textbook since childhood and familiarity flattens everything. Jupiter is not a big planet. Jupiter is a failed star that got most of the way there and stalled. It contains 2.5 times more mass than every other planet, moon, asteroid, and comet in the solar system combined. If you gathered all of them, Saturn, Neptune, Uranus, Earth, Venus, Mars, Mercury, Pluto, Ceres, every rock in the asteroid belt, every body in the Kuiper belt we have found, and rolled them into one, Jupiter would still outweigh the result by a comfortable margin. The Sun holds more than 999 parts in 1,000 of the solar system's mass. Jupiter holds most of the remainder. Everything else, including us, is the rounding error on a rounding error. It is so massive that the Sun does not, strictly speaking, sit at the center of its orbit. The two of them orbit a shared center of mass, and that point lies just outside the Sun's surface. The Sun wobbles around a spot in empty space because Jupiter is there. It is the only planet that does that, and it has a magnetic field that would be the largest structure in the sky if human eyes could see it. 20,000 times stronger than Earth's, generated by an ocean of hydrogen compressed so hard it behaves like a liquid metal, and it inflates a bubble in the solar wind that extends millions of kilometers toward the Sun and, in the other direction, streams past the orbit of Saturn. If that field glowed, it would appear from Earth several times larger than the full moon. That is the object 3I/Atlas was falling toward. And the boundary it grazed, the hill radius, is the edge of the territory over which that object's gravity has the final say. Here is how to think about a Hill sphere. Every body orbiting the Sun holds a region around itself in which its own gravity dominates. Inside that region, you can put a satellite and it will stay. Outside it, the Sun's tidal influence, the difference between the Sun's pull on the satellite and its pull on the planet, is strong enough to peel the satellite away. The size of the region depends on how massive the body is and how far it is from the Sun, and it is generous for distant heavy planets and stingy for close light ones. The Earth's Hill sphere extends about 1.5 million kilometers, which is why the Moon, at 400,000, is comfortably ours. Mercury's is small and tight, which is one reason Mercury has no moons at all. Jupiter, being enormous and being 5 times farther out than we are, gets a Hill sphere 53.5 million kilometers in radius. A sphere 107 million kilometers across. You could fit the entire orbit of Mercury inside Jupiter's zone of gravitational control with room to spare. Every single one of Jupiter's moons lives inside it. And there are 95 of them that we know about, which is itself a fact worth unpacking, because the way that number grows says something about how carefully we watch that part of the sky. 4 of them are the Galilean moons, spotted by Galileo in 1610 with a telescope worse than a modern toy, and they are worlds. Ganymede is larger than the planet Mercury. Callisto is nearly as large. Io is the most volcanically active body in the solar system. Its interior kneaded to melting by tidal forces, throwing sulfur hundreds of kilometers into space. Europa has an ocean of liquid salt water beneath a shell of ice, containing more water than all of Earth's oceans put together, and it is the single most compelling place to look for life within reach of a spacecraft. The other 91 are mostly rubble. Small, dark, irregular chunks of rock a few kilometers across or less, many of them in retrograde orbits far out toward the Hill boundary, clustered into families that share orbital characteristics. The signature of a captured asteroid or comet that was later shattered by an impact, its fragments continuing to orbit together. They are found by taking long exposures with large ground-based telescopes and looking for faint dots that move with Jupiter rather than with the background stars. Teams at the University of Hawaii, at Carnegie, at the Subaru telescope on Mauna Kea have spent decades doing exactly this, and the count creeps up year by year. 92, 95, It will be higher by the time anyone reads this, which is precisely why Loeb's test was a good one. We are actively, systematically, continuously counting Jupiter's moons. The infrastructure to detect a new one already exists and is already pointed in the right direction. If a small object had appeared in a bound orbit after the 16th of March, 2026, we would have found it. Not instantly, because these searches take months of follow-up to confirm an orbit, but eventually and certainly. And a newly bound object appearing days after an interstellar body grazed the Hill boundary would have been, at minimum, the most interesting coincidence in the history of planetary science. Then there are the Lagrange points, which are among the most elegant results in classical mechanics and which almost nobody outside of aerospace ever thinks about. Take any two bodies orbiting each other, the Sun and Jupiter, the Earth and the Moon, Jupiter and one of its moons. In the rotating frame of that pair, there are 5 locations where the gravitational forces and the centrifugal effect balance so that a small third object placed there will stay put relative to the 2 large ones. 3 of them, L1, L2, and L3, sit along the line connecting the 2 bodies, and they are unstable in the way a marble balanced on a saddle is unstable. A small nudge and you drift off, but the drift is slow and correcting it costs almost nothing. 2 of them, L4 and L5, sit 60 degrees ahead of and behind the smaller body in its orbit, and they are genuinely stable, which is why Jupiter has collected 2 enormous swarms of asteroids at those positions. We call them the Trojans. There are over 1 million of them larger than a kilometer. They have been sitting there, held in place by nothing but the geometry of a 3-body problem, since the solar system was young. Humans use Lagrange points constantly. The James Webb Space Telescope orbits the Sun-Earth L2 point, 1.5 million kilometers beyond Earth on the anti-sunward side, because from there the Earth, Moon, and Sun stay in the same direction and a single shield can block all 3, letting the instruments cool to 40 degrees above absolute zero. Solar observatories sit at L1, upstream in the solar wind, giving us early warning of storms. Now put yourself in the position of an engineer, hypothetically, whose objective is to establish a permanent presence at Jupiter, and who is arriving from interstellar space on a hyperbolic pass that will never repeat. Where do you release your hardware? Not close in. The deeper you go into the gravity well, the faster you are moving and the more energy it costs to slow anything down. You want the outer edge, where the escape velocity from Jupiter has dropped to a couple of kilometers per second and orbits are cheap to establish. You want the Lagrange points, where station keeping is nearly free, and those are located near, on the scale of the system, the Hill radius. That is the entire architecture of the argument, and it should be said clearly, it is internally coherent. Given the premise, the geometry follows. The premise is doing an enormous amount of work. It requires a technological civilization, and it requires that civilization to have chosen Jupiter, and it requires the trajectory to have been arranged 10 billion years ago or adjusted in flight. But the engineering logic downstream of it is not stupid, and dismissing it as stupid was one of the ways the skeptical community made itself easy to distrust. There was one more detail, and it was the kind of detail that makes a good story better and a scientific case no stronger. Jupiter's small outer moons have names drawn from Greek mythology, from the lovers and descendants of Zeus, and one of them is Eupheme, a minor figure, the spirit of praise and acclamation, discovered in 2003 and confirmed as a satellite only years later. It is roughly 2 kilometers across. It orbits Jupiter once every 588 days on a retrograde path that carries it far out toward the Hill boundary. And the forecast said that on the 17th of March 2026, one day after closest approach to Jupiter itself, 3I/Atlas would pass within about 30 million kilometers of Eupheme, nearer to that particular 2-kilometer rock than to any other named body in the Jovian system. Eupheme had reached its farthest point from Jupiter on the 23rd of January, 52 days earlier, which is to say it was positioned, at that moment, about as far out along its enormous ellipse as it ever gets. Of 95 moons, one was going to be closest. It was always going to be a coincidence about something. But there is a particular flavor of narrative pleasure in the fact that the moon in question was named for the spirit of acclaim. Set aside, for a moment, every question about what made it. Consider only what it is, physically, as an object, because the physical portrait is available now in more detail than anyone expected, and it is genuinely alien in a sense that has nothing to do with intelligence. Stand on it. It is a thought experiment, but it is a constrained one because we know enough to fill in most of the details. The first thing you would notice is that there is no down. A body 5 kilometers across has a surface gravity somewhere around 1/10,000th of Earth's. Your weight, if you are an average adult, would be measured in grams. A careless push-off would put you into orbit or into space. The escape velocity is a couple of meters per second, roughly the speed of a brisk walk. You could not jump gently enough to stay. Astronauts training for asteroid missions practice with tethers for exactly this reason. The second thing is the color. Cometary nuclei are among the darkest objects in the solar system, reflecting typically 3 or 4% of the light that falls on them. Darker than fresh asphalt, darker than charcoal, comparable to printer toner. This is counterintuitive for something made largely of ice, and the explanation is that the surface is not ice. Billions of years of cosmic ray bombardment break down the simple molecules in the outer layer and reassemble the fragments into complex, carbon-rich organic compounds, tholins, in the general term, which are dark red-brown to black. Every long-exposed surface in the outer solar system is coated in this material. It is the reason Pluto has red patches, the reason the Kuiper Belt objects are ruddy, the reason Comet 67P photographed like a lump of coal. 3I/Atlas spent 10 billion years accumulating that crust. Its outer layer is not ice. It is the most thoroughly irradiated organic chemistry ever to enter our solar system. And beneath it, only meters down, is material that has never been warm. Ever. Since it condensed at under 30 Kelvin in a molecular cloud in a young galaxy, this body has never experienced a temperature high enough to melt water. It has been in the dark at a few degrees above absolute zero for 3/4 of the age of the universe. The heat it absorbed in the autumn of 2025, falling to within 1.36 astronomical units of a G-type star, was very likely the first significant energy input it had received since it was formed. That is what the outgassing was. Not a comet doing its routine. A body being warmed for the first time in 10 billion years, and coming apart at the seams because of it. The surface, during that passage, would have been spectacular and terrifying. Sunlight heats the crust. The crust conducts heat inward. The ice beneath reaches sublimation temperature and turns to gas. The gas builds pressure under a lid of hardened organic material until the lid fails. What follows is a jet, a supersonic outflow through a rupture, carrying dust with it, blasting into vacuum. This is why comet jets are collimated. They are not gentle evaporation. They are pressurized vents, and the vent geometry focuses the flow the way a rocket nozzle does, because the physics is identical. Rosetta watched this happen at 67P for 2 years and recorded the results in detail. Cliffs collapsing, pits opening, a crack across the neck of the nucleus widening measurably over the mission, dust jets switching on at dawn and off at dusk as the rotating body carried each active region into and out of sunlight. Boulders moved. A 100-meter section of cliff face fell. The surface was not stable. It was actively disintegrating. Now scale that up. 67P at its peak was losing a few hundred kilograms per second. 3I/Atlas at perihelion was measured by JUICE at 2,000 kilograms per second of water alone. And the mass budget analysis suggested the total shedding was hard to reconcile with the amount of material a body that size should contain, which is another way of saying it may have been losing a substantial fraction of itself. If you had been standing on it, you would have been standing on a landscape in the process of ripping itself apart, in near total darkness at the surface because the coma above you would have been scattering and absorbing the sunlight, illuminated by a diffuse glow with the sun somewhere behind it as a bright smear. Jets would have been visible as columns of dust catching the light, rising and vanishing into a sky that had no horizon and no blue. And the whole structure, coma, tail, anti-tail, would have extended millions of kilometers above you, a temporary atmosphere 13 times wider than the Earth-Moon distance, held together by nothing, dissipating constantly, replenished from below. Then it would have faded. Past perihelion, the object cooled, the venting slowed, the pressure dropped, and the whole apparatus began shutting down. By March 2026, the light curve was declining steadily. By April, it was a fading dot. By the summer, it was beyond the reach of most instruments. And the deeper question, what does the interior look like, remains open because we never got close enough to find out, and that is the permanent loss. We do not know its rotation period with confidence. We do not know its shape. We do not know whether it is a single coherent body or a rubble pile held together by gravity so weak it barely qualifies as a force. We do not know its density, and density would tell us its porosity, and porosity would tell us how it was assembled, whether it accreted gently, grain by grain, in a quiet disk or violently from collisional debris. We do not know whether it has a layered structure or whether 10 billion years of cosmic ray processing has homogenized the outer hundreds of meters. Every one of those questions would have been answered by a flyby at 1,000 kilometers. Every one of them is now unanswerable forever for this object. That is the cost of not having a spacecraft ready, and it is the strongest argument in the entire story, and it does not require anyone to believe in engineers. And the journey itself, the 10 billion years of it, is worth trying to picture, because interstellar space is not what most people imagine. It is not empty. It is emptier than any vacuum we can produce in a laboratory, roughly 1 atom per cubic centimeter in the diffuse regions, compared to something like 10 to the 19th atoms per cubic centimeter in the air you are breathing, but it is not nothing. It is a thin plasma of hydrogen and helium threaded by magnetic fields, seeded with dust grains, permeated by starlight and by cosmic rays accelerated to relativistic energies by supernova shocks. At 60 kilometers per second, sweeping through that medium for 10 billion years, an object accumulates an enormous integrated dose. Every square centimeter of its surface has been struck by an unimaginable number of particles. The organic crust is the record of that, and the ice a few meters below is the control sample. Unprocessed, pristine, exactly as it condensed, a sealed archive of the chemistry of a molecular cloud that existed when the universe was 3.5 billion years old. We got a partial reading of that archive from the gas it vented. Deuterium ratios, carbon isotopes, carbon dioxide dominance, methanol abundance, nickel chemistry. It is the deepest look into the past that anyone has ever gotten from a physical object, as opposed to from light. And it lasted 1 year, and then the archive closed and left, and it is still leaving. There was, as it happened, a spacecraft already there. Juno arrived at Jupiter on the 4th of July, 2016, after a 5-year cruise, and it did something no mission had done before. It went into a wildly elliptical polar orbit that carried it screaming over the cloud tops every 53 days, closer to the planet than anything had ever flown, and then back out to a safe distance beyond the worst of the radiation. That orbit was not a compromise. It was a survival strategy. Jupiter's magnetosphere is the most violent radiation environment in the solar system, a particle accelerator the size of a star, and Juno's electronics live inside a titanium vault with walls a centimeter thick, and even that only buys time. Every pass degrades the instruments a little more. But Juno had instruments: a near-infrared spectrometer, a magnetometer, a microwave radiometer, a gravity science package, an energetic particle detector, a radio and plasma wave sensor, an ultraviolet spectrograph, and JunoCam, a visible light camera bolted on largely as a public engagement instrument and which turned out to produce some of the most extraordinary images in the history of planetary science. In late July 2025, 3 weeks after the discovery, Loeb published a paper with Adam Hibbard and Adam Crowell of the Initiative for Interstellar Studies, and it was not a philosophical essay. It was orbital mechanics run through professional trajectory optimization software, and it asked a specific question: could Juno be taken out of orbit around Jupiter and thrown at 3I/Atlas? The answer was a qualified yes, and the route was beautiful. You would fire the main engine on the 9th of September 2025 to lower the low point of Juno's orbit, bringing it down to about 2.68 Jupiter radii, skimming the planet. Then, at that low point, deep in Jupiter's gravity well, moving at maximum speed, you would fire again. This is the Oberth maneuver, and it is one of the loveliest results in astronautics, because kinetic energy scales with the square of velocity. A given amount of fuel burned when you are already moving fast buys you far more energy than the same fuel burned when you are moving slowly. It is why every interplanetary mission that can arranges to do its big burns at the bottom of a gravity well. The total velocity change required was 2.6755 kilometers per second, and it would have carried Juno out of Jupiter orbit entirely and onto an intercept with 3I/Atlas on the 14th of March 2026. A flyby, the paper argued, could probe the nature of this object far better than any telescope near Earth. And that is simply true. There is no substitute for proximity. The difference between imaging something from 600 million kilometers and imaging it from a few thousand is the difference between knowing a city exists and walking its streets. There were two problems, and the first was fuel. Juno's remaining propellant was not public. The mission had been extended once already, and its formal end date was the middle of September 2025. The plan being to let it deorbit into Jupiter's atmosphere, the standard end for any spacecraft near a potentially habitable moon, so that nothing terrestrial ever crashes into Europa. That deorbit date, incidentally, was 8 days after the proposed burn. The paper's authors did the honest thing and, unable to obtain the fuel figures even after email exchanges with the Juno team, published their result as a function of the unknown. Here is how close Juno could get for each possible remaining propellant mass. With a full tank and intercept, with 110 kilograms, 5% of the original load, you could still close to within about 27 million kilometers. With less. The second problem was that the entire proposal was, to a certain kind of reader, uncomfortably familiar. A crewed adjacent spacecraft is diverted from its mission to investigate an anomalous object near Jupiter, at the urging of a scientist convinced it is not natural. That is the plot of 2001, A Space Odyssey, and critics said so, and they did not always say it kindly. And yet the idea reached Washington. Representative Anna Paulina Luna of Florida sent a letter to the acting NASA administrator recommending the agency assess Juno's remaining fuel and extend the mission at least through mid-March 2026. At a cost she put at about $15 million per 6 months. $15 million. For context, that is a rounding error in a federal budget, roughly the price of a single F-35 wingtip, and it was being proposed to keep alive the only asset humanity had in position to observe the closest approach of an interstellar object to a planet in recorded history. NASA did not perform the maneuver. The Oberth burn was never executed. The date passed, and in the autumn of 2025, the U.S. federal government entered a shutdown, which added a layer of institutional paralysis to an already narrow window. Loeb complained publicly that he had been unable to get answers about whether the Mars Reconnaissance Orbiter's images of the object during the October flyby would be released, and that silence, in an environment already primed for suspicion, was interpreted by a very large number of people online in the least charitable way available. This is worth sitting with because it is one of the real lessons of the whole affair, and it has nothing to do with aliens. Institutional slowness reads as concealment. A budget office declining to fund a $15 million mission extension is, to an engineer, an entirely ordinary allocation decision made under constraint. To a public watching a once-in-history event go unobserved, it looks like a choice not to look. And when a government shutdown then delays the release of images from a camera that was pointed at the object, the gap between what people expect and what they receive fills up with narrative, and the narrative that fills it is never the boring one. Juno remained in orbit around Jupiter. Its mission was not terminated on schedule. It continued operating into 2026, and it was in position on the 16th of March, and it did observe. But it observed from where it was on the orbit it already had, as a distant spectator rather than a visitor. Loeb noted afterward that the community was still waiting on Juno's data from around that date, and the wait was long, because Juno's data rate is not generous and its priorities are set by a mission plan written years before anyone had heard of 3I/Atlas. But Juno was not the only spacecraft in the neighborhood, and the one that actually delivered was one nobody had planned for at all. The Jupiter Icy Moons Explorer JUICE, to everyone who works on it, launched from French Guiana in April 2023 on a mission to study Ganymede, Callisto, and Europa, the 3 moons of Jupiter that may hold liquid water oceans beneath their ice. It will not arrive until 2031. Getting to Jupiter with the fuel a rocket can lift requires a long, absurd, looping course through the inner solar system, stealing energy from planets in a series of gravity assists, and in the autumn of 2025 JUICE happened to be in a stretch of that cruise that put it in an extraordinary position, close to the Sun on the opposite side from Earth, in the exact region of sky where 3I/Atlas was making its perihelion pass. JUICE could see what Earth could not. What followed was, by the standards of large space agencies, indecently fast. The team switched on 5 science instruments, not a trivial act on a spacecraft in a thermal regime it was never designed to work in, with its high-gain antenna turned toward the Sun and used as a heat shield. Because the big antenna was busy being a parasol, communications had to run through the smaller medium-gain antenna at a fraction of the usual data rate. The observations were taken, and then everyone waited 3 months for the data to trickle home. It arrived in the second-to-last week of February 2026. It was worth it. On the 2nd of November, 2025, 4 days after perihelion, JUICE's Moons and Jupiter Imaging Spectrometer measured the rate at which 3I/Atlas was throwing water into space. 2,000 kilograms per second. 2 metric tons of water vapor every second. The team's chosen comparison, and it is a good one, was 70 Olympic swimming pools per day. Every day, this object was emptying 70 Olympic pools into the vacuum. From an object a few kilometers across. It was a fire hose. JUICE's ultraviolet spectrograph caught the fingerprints of oxygen, hydrogen, and carbon atoms in the surrounding cloud, and traced them outward more than 5 million kilometers from the nucleus. 5 million kilometers. That is 13 times the distance from the Earth to the Moon. The solid body at the center of that structure could fit inside Rhode Island, and its atmosphere reached a third of the way to Mars. And the navigation camera, an instrument built to look at star fields for orientation, a device with no scientific pretensions whatsoever, the spacecraft equivalent of a backup camera, returned an image on the 6th of November that stopped people cold. A bright halo of gas. The nucleus itself invisible inside it, too small and too shrouded. And extending back from the coma, long faint structures. Rays, jets, streams, filaments. Not a smooth fuzzy ball. Structure. Architecture. Pasquale Palumbo of Italy's National Institute for Astrophysics, principal investigator on JUICE's imaging camera, said the images revealed the comet's intense activity around perihelion for the first time, and that they showed an extended coma, a tail, and various morphological structures. Rays, jets, filaments. And in a story where a very large audience was already primed to read intent into geometry, the word jets did a great deal of work. Before Jupiter, there was Mars, and the Mars encounter was in many ways the rehearsal for everything that followed scientifically, politically, and in terms of public temper. On the 3rd of October, 2025, 3I/Atlas passed within 0.19 astronomical units of Mars. 29 million kilometers. That is not close in absolute terms, but Mars is the most heavily instrumented planet in the solar system besides our own, and the fleet in orbit there represents the accumulated investment of half a dozen space agencies over 3 decades. NASA's Mars Reconnaissance Orbiter has been circling since 2006, and its primary camera, HiRISE, is the finest optical instrument ever placed at another world. A half-meter telescope capable of resolving objects the size of a desk on the Martian surface. It was not built to look at comets. It was built to look down. But it can be turned, and pointing it at an object 29 million kilometers away was, in principle, the best chance anyone would have all year to constrain the size of the nucleus, because HiRISE's angular resolution is exceptional, and even a marginally resolved image would have settled the question of whether the solid body was 400 meters or 5 kilometers. ESA's Mars Express, in orbit since 2003, was tasked. The ExoMars Trace Gas Orbiter, a joint ESA-Roscosmos mission designed to sniff out methane in the Martian atmosphere, was tasked, and it returned images. On the surface, the rovers looked up. It was a genuinely global effort, coordinated in weeks, aimed at an object nobody had known existed 90 days earlier. And then the United States federal government shut down. The specific consequence was mundane and the perception of it was not. NASA's public affairs operation went dark. Data releases stopped. Scientists on federal contracts stopped working. And the images from the Mars flyby, the ones everybody was waiting for, the ones that might resolve the size question, sat wherever such things sit while the appropriations fight ran its course. Loeb went on national television and said, in effect, that he had asked about the HiRISE data and had not heard back. For anyone inclined to believe that information was being controlled, that was the confirmation. It was not, of course. It was a budget lapse, one of many in recent decades, with effects that ranged across the entire federal apparatus and had precisely nothing to do with comets. But try explaining an appropriations calendar to an audience that has just watched the most anticipated images in modern planetary science fail to appear on schedule. The explanation is correct, and it is inaudible. The images did come. The size question was not fully settled by them. An object 29 million kilometers away is a very hard target even for HiRISE, and the nucleus remained shrouded inside its own coma, which is the fundamental problem with measuring any active comet. You cannot see the snowball for the snow. Then the object went behind the sun. Perihelion, closest approach to our star, came on the 30th of October, 2025, at 1.36 astronomical units, just inside the orbit of Mars, well outside our own. And at that moment, from Earth's vantage, 3I/Atlas was on the far side of the Sun, in solar conjunction, lost in the glare. This is an entirely routine geometric circumstance. It happens to comets constantly, and it is one of the standard frustrations of the field. It is also, unavoidably, the single most dramatic possible arrangement if you are inclined to see a pattern. The object arranged to be invisible from the one planet with observers on it, during the 1 week when the most would have been happening. What we could see in the run-up and the aftermath was strange enough on its own. The object brightened faster than models predicted, substantially faster, and as it brightened, its color shifted. It turned distinctly bluer than the Sun. That is unusual. Comets are typically reddish, because their dust is reddened by long exposure to cosmic radiation, and because the organic-rich material on their surfaces absorbs blue light. A comet that gets bluer as it heats is a comet that is exposing fresh material from underneath, or one whose emission is being dominated by gas rather than dust. Glowing molecules and atoms fluorescing in sunlight, which happens at specific wavelengths, many of them in the blue. And it was in this window that the non-gravitational acceleration first appeared in the trajectory fits. Meanwhile, other instruments were doing quieter and more valuable work. NASA's SPHEREx mission, an infrared survey telescope launched in 2025 to map the entire sky in over 100 wavelength bands, caught it and delivered spectra. TESS, the transiting exoplanet survey satellite, built to find planets by staring at fields of stars for weeks at a time, turned out to have been staring at a region that contained 3I/Atlas, and the resulting data produced something extraordinary. A continuous 28-hour movie of an interstellar object. Not a series of snapshots. A continuous light curve, long enough to search for rotation, for outbursts, for periodicity. Hubble imaged it repeatedly in July, in November, in the following spring. Webb took its spectrum and found the carbon dioxide dominance. Swift caught the water at 2.9 astronomical units. The Very Large Telescope in Chile found the nickel. ALMA measured the methanol. Subaru photographed it in December. Keck, Gemini, the Nordic Optical Telescope, the Gran Telescopio Canarias. The roll call runs to dozens of the world's largest instruments, plus hundreds of smaller ones, plus an army of amateurs whose contributions to the astrometric arc were substantial and largely uncredited. An Italian amateur named Tony Scarmato, using a 25-centimeter telescope, a 10-inch mirror, the sort of instrument that sits in a shed in a suburban backyard, was still producing usable images of the object in March 2026, stacking 10 2-minute exposures to pull a fading dot out of the noise. That is worth pausing over. A 10-inch telescope, operated by one person, contributing to the observational record of the third interstellar object ever detected, at a moment when it was hundreds of millions of kilometers away and dimming fast. The gap between professional and amateur astronomy has narrowed in the last 20 years to a degree that would astonish anyone who stopped paying attention in the 1990s. That is what the year actually looked like. Not a cover-up. A stampede. Every capable instrument on and above the Earth, plus 2 spacecraft in the outer solar system and a fleet at Mars, pointed at the same faint object, with data flowing into the same archives, analyzed by competing groups on 4 continents who would have loved nothing more than to scoop each other. That is the least concealable activity human beings engage in. The idea that a discovery of artificial origin could have been contained within that system, that thousands of researchers across dozens of institutions in countries that do not trust each other would have coordinated silence, requires a model of human behavior that has never once been observed. And yet the belief persisted and it grew for a reason that is not stupidity. It grew because the alternative on offer was a comet, and a comet felt like a brush-off. Felt like being told to go home. The tragedy, and it is a small tragedy but a real one, is that the comet was the astonishing part, and nobody managed to say so loudly enough. The strangest structure of all had shown up months earlier, and it never fully went away. Comets have tails that point away from the sun. This is not a suggestion, it is a consequence of physics. The tail is made of material blown backward by radiation pressure and the solar wind, so it streams away from the light source regardless of which direction the comet is traveling. A comet heading toward the sun has its tail in front of it. A comet heading away has it behind. The tail is a windsock, and the wind always blows outward. 3I/Atlas had a feature pointing the wrong way. a sunward extension, an antitail. Antitails are not unprecedented. There is a well-known geometric illusion that produces them. When Earth crosses the plane of a comet's orbit, a fan of large, heavy dust grains that were shed slowly and never got blown far can appear, in projection, to stick out toward the sun. It looks like a spike. It is a trick of perspective, and it resolves itself as the viewing geometry changes. The problem was that this one did not resolve neatly. Analysis of the Hubble image from the 21st of July, 2025 suggested that the pre-perihelion antitail was not a broad fan seen edge-on but something narrow, a collimated jet aimed at the sun, roughly 10 times longer than it was wide. And collimation is the operative word, because it recurred. Post-perihelion imaging showed the same tight, focused geometry extending hundreds of thousands of kilometers. Whatever was venting from this object was not venting the way a garden sprinkler vents. It was venting the way a nozzle vents. There are natural explanations. Comets develop active regions, patches where the insulating crust of dust has cracked open and volatiles beneath can sublimate directly, and a rotating nucleus with a small active vent will produce a beam of gas and dust that sweeps around like a lighthouse and, integrated over time, looks like a structured jet. This is standard cometary behavior. It was photographed in exquisite detail at Comet 67P by the Rosetta mission, which spent 2 years watching jets switch on and off across a landscape of cliffs and pits. Collimation happens. It happens for boring reasons. But it is not hard to see how a sunward-pointing, 10-to-1 collimated beam of material on an object that has already accumulated 20 other unexplained properties reads to a mind looking for intent. And then came the acceleration argument, which is the most technically interesting part of the whole story and also the part where the public discussion went most thoroughly off the rails, because the claim reversed itself completely and both versions got used as evidence for the same conclusion. Here is the physics. When gas escapes a comet's nucleus, the nucleus recoils. It is a rocket, an extremely inefficient one, thrusting in whatever direction its vents happen to face. Over months, that produces a measurable deviation from a pure gravitational path, and this non-gravitational acceleration is routinely measured for comets and routinely used to estimate their masses, because the size of the deviation depends on how much mass is being pushed by how much thrust. Big push, small object, large deviation. Same push, huge object, negligible deviation. Through the summer and early autumn of 2025, with more than 4,000 astrometric positions in hand, the trajectory fit came back clean. The residuals were consistent with pure gravity. Any non-gravitational acceleration was below a very tight limit. And that was strange because the object was demonstrably venting enormous quantities of material, 150 kilograms per second by the JWST measurement, 2,000 per second at its peak by juices. A fire hose that produces no recoil means one of two things. Either the thrust is balanced by other thrust in the opposite direction, or the thing being pushed is far more massive than it looks. Take the second interpretation and run the numbers, and you get a nucleus of 5 kilometers and a mass north of 33 billion tons. 33 trillion kilograms. Loeb's argument at that stage was, this object is anomalously, impossibly massive for an interstellar wanderer, and the galaxy cannot supply enough rocky material to make such an object a plausible random draw. Then, at the end of October 2025, a JPL navigation engineer named Davide Farnocchia filed an updated solution, and the object had started accelerating. Near perihelion, a non-gravitational term appeared in the fit for the first time. Now, the mundane reading is completely obvious. The object had just made its closest approach to the sun, its activity had spiked dramatically, it was brightening at an unexpected rate and turning distinctly bluer, and a comet that suddenly starts venting hard suddenly starts feeling recoil. That is what comets do. It is the least surprising possible development. Loeb himself wrote that the acceleration was likely the result of massive mass loss and an elongating plume. And then he added the alternative. The non-gravitational acceleration might be the technological signature of an internal engine. Consider what has happened to the argument at this point. No acceleration was evidence of anomalous mass, which was evidence of something unnatural. Acceleration was evidence of a possible engine, which was evidence of something unnatural. Both branches of a binary outcome had been assigned to the same conclusion in advance, and this is the precise structural feature that makes a hypothesis unfalsifiable. It is not dishonest. Loeb was open about both readings and never hid the mundane one. But once a framework can absorb any result, it has stopped being a scientific instrument and become a lens. Meanwhile, the isotope results arrived, and they were, by any reasonable standard, the most genuinely important scientific findings of the entire encounter, and they are what almost nobody was talking about. Hydrogen comes in two stable forms. Ordinary hydrogen has one proton in its nucleus. Deuterium has a proton and a neutron, making it twice as heavy, and water made with deuterium is heavy water. The ratio of deuterium to ordinary hydrogen in a body of water is a fingerprint of the temperature at which that water froze, because the chemical reactions that build water molecules in cold interstellar clouds preferentially incorporate deuterium, and the colder the cloud, the stronger the preference. It is a thermometer that has been running since before the sun existed, and reading it tells you where and when a piece of ice was assembled. The deuterium to hydrogen ratio in the water of 3I/Atlas came in at about 0.98%. Roughly 1 deuterium atom for every 100 ordinary hydrogens. That is around 30 times the value in typical solar system bodies. In the methane, the enrichment was more extreme still, roughly 1 in 30. Trace carbon, 13 signatures pointed the same direction. The interpretation from teams at NASA and ESA was that this water froze in an environment below 30 Kelvin, colder than -240 degrees Celsius, colder than almost anything in our own system's history, a temperature you find in the dense cores of molecular clouds where starlight has been almost entirely extinguished by dust. And running the chemistry backward gave an age. 10 to 12 billion years. Formed at what astronomers call cosmic noon, the era when the universe was at its most furiously productive, building stars faster than at any time before or since, back when the Milky Way was a rougher and hotter and more chaotic place. Martin Cordiner, one of the scientists on the work, described it as an ancient object probably predating our sun and our solar system. The universe itself is 13.8 billion years old. This thing had been in existence for 3/4 of that, which means that when the light from Atlas's telescope in Chile fell on a detector on the 1st of July, 2025, humanity made physical contact with a piece of matter that had been drifting between the stars since before the Earth, before the sun, before the elements in your body had been assembled in stars that had not yet been born. It watched the Milky Way's spiral arms form. It was already ancient when our solar system's first grains condensed. Nothing in the alien technology hypothesis is a fraction as remarkable as that, and it was verified, published, and peer-reviewed, and it moved a rounding error of the attention that the word aliens moved. That asymmetry is not a criticism of the public. It is a fact about what stories are, and any honest account of this year has to include it. There was more. ALMA, the Atacama Large Millimeter Array, 66 radio dishes on a Chilean plateau 3 miles above sea level, measured record methanol abundances. There was a mass budget discrepancy. The total quantity of material the object appeared to be shedding, integrated over its passage, was difficult to reconcile with the amount of material a nucleus of the estimated size should contain. It was, by some accountings, spending more than it had. And through all of it, the object kept moving toward the 16th of March, and the number 53.5 million kilometers kept sitting there, and the world kept waiting to find out whether Jupiter would wake up one morning with a 96th moon. There is a version of the extraordinary claim question that does not require any engineers at all, and it is the one that will still be a live scientific issue in 50 years. In June 2026, Loeb appeared on television and raised the methane. The object's methane was extraordinarily enriched in deuterium, roughly 1 heavy hydrogen atom in every 30, an enrichment far beyond anything in our solar system. And methane on Earth is a molecule with a complicated rhizome. A great deal of it is produced geologically. A great deal more of it is produced by living things. Methanogens, microorganisms that generate methane as a metabolic byproduct, have been doing this for something like 3.5 billion years, and they are among the oldest branches on the tree of life. When planetary scientists spent 2 decades and billions of dollars hunting for methane in the atmosphere of Mars, that is why. So the question was posed: is it indicative that there are microbes in this iceberg? The scientific consensus, from NASA and from essentially every specialist who addressed it, was firm and unglamorous. The methane is chemistry. Cold, dark, radiation-driven chemistry of a kind that has been studied in laboratories for decades and observed in interstellar clouds for longer. You do not need life to make methane, you need carbon, hydrogen, low temperature, and time, and 3I/Atlas had all three in abundance and 10 billion years of the fourth. But the deeper question underneath it does not go away, and it is not fringe. It is called panspermia, and it is one of the oldest ideas in the philosophy of biology, the hypothesis that life or its precursors moves between worlds, not as a designed act, as debris. The case for taking it seriously has strengthened considerably in the last 30 years, for reasons that have nothing to do with wishful thinking. We know that impacts eject material from planetary surfaces at escape velocity. We have meteorites on Earth that are demonstrably from Mars, blasted off by asteroid strikes and eventually intercepted by our own gravity. We know that some microorganisms survive conditions that seem impossible: vacuum, extreme cold, doses of radiation that would kill a human hundreds of times over, and durations measured in years. We know that the interiors of rocks provide substantial shielding. And we know now that the building blocks are common. Amino acids have been found in meteorites. Sugars have been found in meteorites. The Rosetta mission detected glycine, the simplest amino acid, in the coma of Comet 67P. Complex organic chemistry is not rare in the universe. It is close to universal. What was missing from the picture was a courier. Something moving between star systems, carrying material on timescales that make the transfer plausible. 3I/Atlas is a courier. Whatever else it is a 5-kilometer body of ancient carbon chemistry, moving at 60 kilometers per second, that has crossed an enormous fraction of the Milky Way and arrived here intact enough to still be venting volatiles. Came from somewhere. It is going somewhere else. And it is the third one we have found in 8 years, which means the traffic is heavy. Estimates put the standing population of interstellar objects inside Neptune's orbit at any given moment in the range of 1 at all times, which integrated across the history of the solar system means billions of visits. Whether any of them ever carried anything alive is entirely unknown. The odds against surviving 10 billion years of cosmic ray exposure are formidable, and nothing in the 3I/Atlas data speaks to biology one way or the other. But the mechanism is no longer hypothetical. The couriers exist. We have photographed 3 of them. And there is a related idea that Loeb raised in the spring of 2026 which is genuinely delightful and which has nothing to do with aliens visiting us, because it is about us visiting them. 3I/Atlas was moving at roughly 60 kilometers per second on its way out. That is more than twice the speed of the fastest object humans have ever launched. Voyager 1, after 48 years, is doing about 17 kilometers per second. New Horizons is slower. The reason is straightforward. It is fantastically expensive to accelerate mass, and chemical rockets are limited by the energy density of chemical bonds, and we have essentially maxed out that technology. But an object passing through at 60 kilometers per second is free momentum. If you could get a spacecraft alongside, matching its trajectory closely enough to land on it or even just to attach, you would have a ride out of the solar system faster than anything we can build, powered by an engine that ran 10 billion years ago in another star system. You could plant an instrument package. You could plant a time capsule. You could, if you were feeling grandiose about it, plant a sample of terrestrial biology and let the galaxy sort out the rest. 3I/Atlas was, by a remarkable stroke of luck, an ideal candidate for this, a retrograde orbit within 5 degrees of the ecliptic plane, which is to say almost exactly in the plane where all our launch vehicles operate. Loeb pointed this out repeatedly, and the answer every time was that we could not have done it, because we did not know it was coming until it was already inside the orbit of Jupiter and closing fast, and building an interceptor takes years. That is the real lesson of the missed opportunity, and it has nothing to do with what the object was. It is that we currently have no capability to respond to a discovery on a timescale of months, and the objects that matter most give us exactly that much notice. Meanwhile, the chemistry has already told us something enormous about the galaxy, and it deserves to be stated plainly because it is the actual scientific payload of this entire year. We now have a direct chemical sample of the material from which planets formed around another star, at an epoch when the universe was a quarter of its current age. Not an inference from starlight, not a model, a measurement of the isotope ratios in the actual ice. And what it says is that the water in that ancient system froze colder than the water in ours, that it carries a different hydrogen signature, that its carbon monoxide inventory was richer, that its nickel chemistry ran a different course. It says the raw materials of worlds around 10-billion-year-old stars were not identical to ours. Everything we believe about how common planets are, how common habitable ones might be, how common the chemistry of life might be, rests on the assumption that our solar system's formation is broadly representative. That assumption is now, for the first time, subject to a direct test using a physical sample from somewhere else. One sample, but we had 0 before, and 1 is an infinitely larger number than 0, which raises the question everybody asks eventually, and which has a genuinely frustrating answer. Where did it come from? The intuition is that this should be solvable. We know its velocity vector to extraordinary precision. We know the positions and motions of over 1 billion stars, thanks to the European Space Agency's Gaia mission, which spent a decade measuring the distances and proper motions of the Milky Way's stellar population with an accuracy equivalent to measuring the width of a human hair from 1,000 kilometers away. Run the object's trajectory backward. Run the stars backward. Look for a close pass. Find the home system. It does not work, and the reason it does not work is a lesson in the limits of prediction. The Milky Way is not a rigid structure. It is a fluid, differentially rotating, gravitationally lumpy system in which every star's path is perturbed by every gas cloud it passes, every spiral arm density wave it crosses, every other star that happens by. Integrate an orbit backward through that for a few million years and the answer stays reasonably trustworthy. Integrate for 100 million and the uncertainties begin to swamp you. Integrate for 10 billion years and you are not doing astronomy anymore, you are doing chaos theory, and the answer is a probability cloud that covers the galaxy. For Oumuamua and Borisov, both apparently younger, backward integration produced short lists of candidate stars that might have been passed within a few million years, not origin systems, just recent neighbors. For 3I/Atlas, with an age of 10 to 12 billion years, the exercise is meaningless. This parent star is almost certainly dead. If it was massive, it exploded and its remnant is a neutron star or a black hole drifting somewhere. If it was sun-like, it exhausted its hydrogen, swelled into a red giant, shed its outer layers into a planetary nebula that has long since dispersed, and left behind a white dwarf cooling slowly toward invisibility. If it was small and red, it may still be burning. Red dwarfs live for trillions of years, but it has moved so far and been so perturbed that identifying it is hopeless. What we can say is statistical, and it comes from the velocity. Stars in the Milky Way sort into populations. The thin disk, where the sun lives, is a flattened layer of relatively young, metal-rich stars moving on near-circular orbits with modest vertical excursions. The thick disk is older, more metal-poor, puffed out above and below, its members moving faster relative to the local standard of rest because they have been gravitationally stirred for billions of years. The halo is older still, a nearly spherical distribution of ancient stars on wild plunging orbits, some of them accreted from small galaxies the Milky Way devoured long ago. The velocity of 3I/Atlas marks it as thick disk. Old population, formed when the galaxy was young and building itself out of turbulent gas, before the elegant spiral structure we see today had settled into place. It approached from the direction of Sagittarius, the direction of the galactic center, though that is a projection effect rather than a statement about origin. So the honest answer to where did it come from is, from a star that no longer exists in a version of this galaxy that no longer exists, and we will never know which one. There is something about that which is more affecting than any specific answer would have been. And the mechanism of its ejection is at least well understood, because we have watched it happen in simulations thousands of times and we have seen the aftermath in the debris disks around other stars. A young planetary system is a violent place. Out of a collapsing cloud of gas and dust, a star ignites at the center, and around it a disk of leftover material begins to condense into solids. Dust grains sticking to dust grains, pebbles to pebbles, boulders to boulders, in a runaway process that builds planetesimals in a geologically brief span. Most of that material never becomes a planet. It stays as rubble. And the objects that do become planets, particularly the giant ones, are gravitational bullies of extraordinary efficiency. A giant planet forming in the outer part of a young system will, over millions of years, encounter enormous numbers of smaller bodies. Each encounter exchanges energy. Some bodies get flung inward, some get thrown into eccentric orbits, and a substantial fraction, perhaps most of the original planetesimal population, gets accelerated past the escape velocity of the entire system and hurled into interstellar space. Our own solar system did this. The Oort cloud, the enormous spherical reservoir of comets that surrounds the Sun out to something like 50,000 astronomical units, is thought to be the population that got flung outward but not quite hard enough to leave. Every long-period comet we have ever seen came from there. And for every object that ended up in the Oort cloud, models suggest several more crossed the line and left entirely. Those objects are out there now, drifting between the stars, and some of them will pass through other systems, and any astronomers in those systems who are watching carefully will one day flag a moving dot with an eccentricity above one. We have exported comets. It would be strange if we had not imported any. 3I/Atlas is a receipt from that exchange. It is a piece of another system's construction debris, ejected by a planet we will never see, from a star that died before our own was born, and it spent the entire subsequent history of the universe in transit, and it happened to pass through the one solar system in this arm of the galaxy that has, for the last century or so, been operating telescopes. The timing of that is the actual coincidence worth marveling at, and it has nothing to do with Hill radii. This object has been traveling for 10 billion years. Our capacity to detect it has existed for about 10. If it had arrived in 1990, we would have missed it entirely. The surveys did not exist. If it had arrived in 1890, nobody could have found it with any instrument on Earth. If it had arrived in the year 800 or 40,000 BC, or during the Cretaceous, it would have swept through, thrown its 70 Olympic pools a day into the vacuum, rounded the Sun, grazed Jupiter's Hill sphere, and departed with no more record of its passage than a rearrangement of dust. 10 billion years of travel. A 10-year window of observation. And it arrived inside the window. That, if you want a genuinely staggering coincidence, is the one. Except that it is not a coincidence at all, and understanding why is the last piece of the statistical argument. We did not detect it because it was special. We detected it because we finally built the machines that detect things. The traffic has always been there. Billions of interstellar objects have passed through the solar system since the Earth formed. What changed in the last decade is not the sky. It is us. We turned on the lights, and we started seeing what had always been walking past. 3 in 8 years. It is not the beginning of an arrival. It is the beginning of our ability to notice. To understand why most working astronomers never lost a night of sleep over any of this, you have to understand something about probability that is genuinely counterintuitive and that human brains are constructed to get wrong. Take the 1 in 25,000. The claim is that 3I/Atlas's closest approach to Jupiter matching Jupiter's Hill radius to a fraction of a percent is a coincidence so unlikely that design becomes a serious candidate. And stated that way, in isolation, it sounds compelling. 1 in 25,000 is a real number. It is longer odds than getting struck by lightning in a given year. But consider how the question was asked. The trajectory of 3I/Atlas was fixed by the time we discovered it. It was going to pass Jupiter at some distance. That distance was going to be some number. And once you have a number, you can go looking through the enormous catalog of other numbers associated with Jupiter to see whether any of them are close to it. Jupiter's Hill radius. Jupiter's orbital radius. The semi-major axis of any of its 95 moons. The distance to any of its 5 Lagrange points. The radius at which its magnetotail terminates. The distance at which the Galilean resonances break down. There are dozens of characteristic distances associated with Jupiter, spread across many orders of magnitude, and a match to any of them would have been reported as the coincidence. This is what statisticians call the look elsewhere effect, and it is the reason particle physicists demand 5 sigma evidence before announcing a discovery, because if you scan enough of a spectrum, 3 sigma bumps appear everywhere for free forever. There is an even older name for the informal version: the Texas sharpshooter fallacy. A man fires a rifle at the side of a barn, walks up, finds the tightest cluster of holes, and paints a bullseye around it. He is now an excellent marksman. The shots were random. The target was drawn afterward. And the same analysis dismantles the rest of the geometric list, one item at a time. The odds of arriving within 5 degrees of the ecliptic are 1 in 500. But why 5 degrees? Because that is where it arrived. Had it arrived at 40 degrees, nobody would have computed the odds of arriving within 40 degrees. The odds of passing near Mars, Venus, and Jupiter are small, but any trajectory through the inner solar system passes near something, and the planets, being spread around the ecliptic and orbiting continuously, guarantee that any object moving in that plane will make some close approaches. The odds of being hidden behind the Sun at perihelion are small, but perihelion happens somewhere, and there is a substantial fraction of the sky in which Earth cannot observe an object well at any given moment, and a solar conjunction is an ordinary nuisance that interferes with observations of ordinary objects constantly. The deeper point is that these probabilities were computed after the fact, on outcomes already observed, and then multiplied together as though they were independent tests specified in advance. That is not how probability works. If you flip a coin 20 times, the specific sequence you get has a probability of 1 in about a million. That does not mean the coin was intelligently designed. Every sequence has that probability. Something with a probability of 1 in a million happens every single time you flip a coin 20 times. And the chemistry, the nickel without iron, the item that carried the most rhetorical weight because it evoked a smelter, has a specific and rather beautiful natural explanation that was published within months. Nickel forms a compound called nickel tetracarbonyl, one nickel atom bonded to 4 carbon monoxide molecules. It is a genuinely strange substance, a metal compound that is volatile at low temperature, which is unusual enough that industrial chemists exploit it in the Mond process to purify nickel from ore. It is also unstable in sunlight. Ultraviolet photons break it apart, releasing free nickel atoms into the gas. Iron does not form an equivalent compound under the same conditions. So a cold, carbon monoxide-rich comet, and 3I/Atlas was extraordinarily rich in carbon oxides, will naturally release nickel vapor without iron vapor at low temperatures purely through photochemistry. The signature that looked like industry is a signature of exactly the kind of frigid, CO-saturated formation environment that every other measurement independently pointed to. The anomalies were not separate anomalies. They were the same fact viewed from different instruments. That is the pattern, and it holds across most of the list. The carbon dioxide dominance, the deuterium enrichment, the carbon-13 signature, the nickel chemistry, the early activity far from the Sun, all of these are what you would predict for an object assembled at extremely low temperature, in a carbon monoxide-rich cloud, an enormously long time ago in a galaxy chemically different from the one we live in. The anomalies are not 22 independent 1 in 1,000 events. They are one fact: this thing is very old and formed very cold somewhere else, expressed 22 ways. Multiplying their individual improbabilities together, as though each were an independent coin flip, produces astronomical numbers that mean nothing at all. And the mass? The mass is the one that most deserves a second look, because the argument that the galaxy cannot afford an object this large rests on an assumption about the population of interstellar objects that is derived from a sample of 3. Our detection surveys are enormously biased toward large, bright, active objects. We find what we can see, and we can see big things. It is entirely possible that interstellar objects the size of Oumuamua outnumber ones the size of 3I/Atlas by a factor of 1 billion, and we found the big one first because the small ones are invisible. Selection effects in a sample of 3 are not a foundation on which to overturn planetary formation theory, let alone to invoke engineers. None of which proves anything. That is the honest position, and it is the position that the great majority of astronomers actually held throughout. Not that the alien hypothesis was refuted, but that it was unnecessary. Every observation had a natural explanation available, and most had a natural explanation that was independently supported by other observations, and a hypothesis that explains nothing better than the existing one and requires the existence of a technological civilization is not a hypothesis you adopt. Which brings us to the title of this story and to the double meaning buried inside it. Hiding in plain sight, there is the reading everyone reaches for first, that the object was a machine, disguised as a comet, and that the disguise worked. But there is a second reading, and it is the one that a very large number of scientists would have offered if asked. What was hiding in plain sight was the ordinary explanation. It was there the whole time, unglamorous, fully adequate, sitting in the open where anyone could pick it up, and it was almost impossible to see because the alternative was so much more interesting. The most extraordinary object ever to visit our solar system was a comet from a star that died before the Earth was born, and that was somehow not enough. And there is a third reading, which is the darkest and which is about us rather than about the object. What was hiding in plain sight was the way the argument was constructed. The pattern of assigning both outcomes of a test to the same conclusion. The habit of computing probabilities after the results are known. The steady accumulation of a list that grew longer as more data arrived, when a hypothesis that was correct should have produced a list that got shorter. That structure was on public display, time-stamped, published in the open, for anyone to examine. It was hiding in plain sight too. But it is very important to be fair here because there is a version of this narrative that congratulates the establishment and treats the skeptic as a fool, and that version is false and it is lazy and it would have been a disaster if it had been adopted as policy. Because Loeb was right about something fundamental, and it is this: the appropriate response to an interstellar object is to go look hard, with everything, immediately, whatever your prior on the technological hypothesis, and a reasonable prior is very, very low. The cost of taking the possibility seriously enough to point instruments at it is trivially small, and the cost of not looking is the permanent, irrecoverable loss of the data. 3I/Atlas is gone. It will not come back. Whatever we did not measure in that window is unmeasured forever. $15 million to keep Juno alive was, in that light, an obvious bet. And that argument won. Not the alien hypothesis that lost decisively, but the argument for aggressive, immediate, unembarrassed investigation. That is why JUICE's teams scrambled 5 instruments on a spacecraft in a thermal regime it was not designed for. That is why Hubble and Webb and Swift and SphereX and the Very Large Telescope and ALMA and Subaru and Keck and Tess and a large fraction of the world's professional astronomy all pointed at the same faint smudge. And it is why, in the spring of 2026, a group of scientists in Northern California spent 7 hours listening. It would be dishonest to pretend that the professional community handled this gracefully, because in significant respects it did not. The dominant register of the response was exasperation. Astronomers who had spent their careers on cometary science watched a colleague from a different subfield generate more coverage for a technological hypothesis than they could generate for a decade of results, and they were not gracious about it. The exchanges got personal. When Loeb's non-gravitational acceleration argument was publicly criticized by a prominent science communicator, Loeb responded not by addressing the substance but by pointing out that he had published 11 papers on 3I/Atlas in the same period and that his critic had published none, and by challenging him to explain the 9 anomalies then on the list, and by noting that scientific truth is not decided by popularity contest. That is a fair point wrapped around an unfair one, and both sides were doing the same thing. Loeb had a genuine grievance. Dismissal is not refutation, and a great deal of what was said about him consisted of tone rather than analysis. His critics had a genuine grievance too. A public that cannot evaluate technical arguments will resolve a dispute between a Harvard professor and an anonymous consensus in favor of the Harvard professor, and the resulting distortion of the public understanding of what astronomers actually think is a real cost borne by people who did nothing to earn it. And underneath the personalities is an institutional problem that this episode illuminated with unusual clarity. Modern science operates on a set of incentives that are almost perfectly designed to suppress the discussion of low-probability, high-impact hypotheses. Funding is allocated by peer review, and peer review rewards proposals that promise incremental, achievable results in established areas. Tenure is awarded for a record of publication in respected venues, and respected venues are conservative. Careers are built by not being embarrassing. Every structural force in the profession pushes a young researcher towards safe questions, and the people who tell you this is not true are almost always people who already have tenure. Loeb's argument, and this is the part of his case that survives everything, is that this creates a systematic blind spot. Not a conspiracy, a selection effect. If the only hypotheses that get investigated are the ones that are safe to investigate, then any phenomenon whose true explanation is unsafe will go permanently unexplained, and nobody will notice because the absence of research is invisible. He is not wrong about that. Whether the technological origin of interstellar objects is a hypothesis that deserves the specific weight he assigned it is a separate question, and the answer is probably no. But the meta-argument that the profession needs someone willing to say unpopular things and absorb the reputational damage is sound, and the profession's response to him has frequently proven his point about how it treats such people. At the same time, and this must be said with equal force, there is a difference between defending the right to raise an unpopular hypothesis and defending a particular hypothesis after its test has failed. The Jupiter prediction was made. It was specific. Failed. The intellectually complete version of this story requires that failure to be registered with the same volume as the original claim, and in the general noise of the discourse it mostly was not. New arguments appeared. New anomalies were added to the list. The count went from 8 to 9 to 22, and a list that grows in response to disconfirming evidence is behaving less like a hypothesis and more like a commitment. There is a name for this in the philosophy of science, and it comes from Imre Lakatos, who was interested in why theories do not die when a single prediction fails. His answer was that scientists protect a theory's core by adjusting the assumptions around the edges, and that this is often entirely legitimate. Newtonian mechanics predicted the wrong orbit for Uranus, and rather than abandoning Newton, astronomers postulated an unseen planet perturbing it. They found Neptune. The auxiliary hypothesis was correct, and the core theory was saved, and everyone was right. But the same maneuver applied to Mercury's orbital anomaly produced a predicted planet called Vulcan, which was searched for exhaustively and does not exist, and the anomaly was eventually resolved by throwing out Newton's core and replacing it with general relativity. The difference between a progressive research program and a degenerating one, in Lakatos's framing, is whether the adjustments generate new predictions that turn out to be true, or whether they only ever absorb failures after the fact. That is the test to apply here, and it is a test that can only be applied over time. What is undeniable is that a great deal of good came out of the argument regardless of who won it. Because of the pressure, ESA scrambled instruments on a spacecraft in a thermal regime it was never rated for and got measurements nobody had planned to take. Because of the pressure, a member of Congress read a letter about orbital mechanics into the record, and a $15 million mission extension got a hearing it would otherwise never have received. Because of the pressure, the SETI Institute conducted the most sensitive technosignature search ever performed on a solar system object and established detection limits that will be the benchmark for the next decade. Because of the pressure, JWST time was allocated, ALMA time was allocated, Hubble time was allocated, and the isotopic measurements that established this as the oldest object ever studied by humans got made in a window that would otherwise have closed. Attention is a resource. It is allocated irrationally, by narrative rather than by merit, and this is usually a disaster. Occasionally the narrative points at something that deserves it anyway, and the irrational allocation produces a rational outcome. And there is one more thing that came out of it, which is harder to quantify and which may matter more than any of the science. For about a year, an enormous number of people who do not follow astronomy learned what eccentricity is. They learned what a Hill sphere is. They learned why comets have tails that point away from the sun, and what deuterium is, and what a Lagrange point does, and why you cannot just turn a spacecraft around. They learned these things because they wanted to follow an argument about aliens, and in the course of following it they absorbed a considerable amount of orbital mechanics and physical chemistry. That is not nothing. The number of Americans who could correctly explain what makes an orbit hyperbolic went up measurably in 2025 and 2026, and it went up because a Harvard astronomer said something that most of his colleagues thought was wrong. There are worse legacies, so let us go through it properly, not dismissively and not credulously. Item by item, with the best case for strangeness stated fairly and the best natural explanation stated alongside it, because that is the only honest way to close an argument of this kind. The trajectory alignment with the ecliptic plane. Arriving within 5 degrees of the plane of the planets, on a retrograde orbit with roughly 1 in 500 odds against. The natural answer is that the probability was computed after the arrival was observed, and that we have a sample of 3, and one of the 3 arrived steeply inclined while another arrived at a moderate angle. A 1 in 500 event in a sample of 3 is unremarkable if you did not specify in advance which of the many possible geometric properties would count. Verdict. Not evidence, though it is genuinely a lucky break for observers because it put the object in the plane where our spacecraft operate. The fine-tuned arrival times near Mars, Venus, and Jupiter. The natural answer is that an object moving in the ecliptic plane at a modest inclination cannot avoid making close approaches to planets, because the planets fill that plane and orbit continuously. Encounters are the default outcome of that geometry, not a surprise. Verdict. Not evidence. The perihelion occurring in solar conjunction. The natural answer is that roughly a fifth of all perihelion positions are unfavorable from Earth for a body of this orbit, and that solar conjunction is a routine and constant nuisance in observational astronomy. Verdict. Not evidence, though it was a genuine and costly misfortune. The Hill radius match at Jupiter. The most striking item on the list at 1 in 25,000. The natural answer is the look elsewhere effect. Many characteristic distances are associated with Jupiter, spanning orders of magnitude, and any match to any of them would have been reported. Verdict: not evidence, but the best constructed item on the list and the one that produced a genuine falsifiable prediction which was tested and failed. The anomalous mass. A nucleus possibly 5 kilometers across and 33 billion tons. 1,000,000 times more massive than Oumuamua, apparently exceeding what the galaxy's supply of interstellar rubble should allow. The natural answer is that the mass estimate depends on the non-gravitational acceleration measurement, which was near the detection limit and which changed when the object became more active, that the size range from Hubble spanned a factor of 12, that our detection surveys are heavily biased toward finding large bright objects, and that a population model built on 3 detections has error bars wide enough to accommodate almost anything. Verdict: genuinely interesting, unresolved, and probably a selection effect. The extreme speed, 58 kilometers per second, faster than either predecessor. The natural answer is that this is the expected velocity for a thick disk object, and it corroborates the great age independently derived from the isotopes. Verdict: not an anomaly at all. It is a measurement and a very useful one. The carbon dioxide dominance in the coma, among the highest CO2 to water ratios ever measured. The natural answer is formation at extremely low temperature, in an environment rich in carbon oxides, which is exactly what the deuterium and carbon-13 measurements independently indicate. Verdict: not an anomaly. It is a consistency check that passed. Nickel without iron. The item that carried the most rhetorical force, because nickel without iron evokes industrial refining. The natural answer, published within months, is nickel tetracarbonyl photodissociation. Nickel forms a volatile carbonyl compound at low temperature. Iron does not under the same conditions, and ultraviolet sunlight liberates free nickel atoms from it. In a carbon monoxide-rich comet, this is the predicted outcome. Verdict: explained, and explained by the same cold CO-rich formation environment that explains 3 other items on the list. Early activity at large heliocentric distance, venting water at 2.9 astronomical units, and showing a coma at 4.85. The natural answer is that a body with abundant carbon dioxide and carbon monoxide will begin activity far beyond the water sublimation line, because those species sublimate at much lower temperatures, and that the resulting gas flow drags water-bearing dust with it. Verdict: explained by the composition. The antitail, a sunward-pointing collimated jet, 10 times longer than wide. The natural answer is the standard projection effect for large slow dust grains combined with genuine collimated venting from an active region, both of which are documented in solar system comets and were imaged directly at 67p. Verdict: unusual in degree, ordinary in kind. The absence of non-gravitational acceleration, and then its presence. The natural answer is that a massive nucleus produces little recoil until activity spikes near perihelion, at which point recoil becomes measurable. This is textbook cometary behavior, and the 2 observations are not in tension. They are a sequence. Verdict: not an anomaly, and the fact that both the presence and the absence were offered as evidence for the same conclusion is the single most telling structural feature of the whole case. The extreme deuterium enrichment, 30 times solar system values in water, more still in methane. The natural answer is formation below 30 Kelvin in a dense cloud core, giving an age of 10 to 12 billion years. Verdict: the most important result of the entire encounter, and not an anomaly in the sense intended. It is a spectacular and coherent finding that makes the object more interesting, not more suspicious. The record methanol, explained by the same cold chemistry. The mass budget discrepancy, genuinely unresolved, and dependent on a nucleus size we never measured. The brightening and bluing near perihelion, explained by fresh material exposure and gas fluorescence. The rays, jets, streams, and filaments in the juice imagery, explained by discrete active regions on a rotating nucleus. Add them up honestly and the picture is not 22 independent improbabilities. It is one central fact, an extremely old, extremely cold-formed, carbon oxide-rich body from a chemically different era of the galaxy, expressed through a dozen instruments, plus a handful of geometric coincidences computed after the fact, plus 2 or 3 items that remain genuinely open, and that would have been resolved by a close flyby we did not have the capability to perform. That is the verdict. It is not a triumphant one, and it should not be delivered triumphantly. It is a comet, an extraordinary comet, the oldest thing we have ever touched with an instrument, but a comet. And the reason it took a year and a global argument to establish that is not that anyone was hiding anything. It is that establishing things is slow, and the object was fast. The Allen Telescope Array sits in a high valley at Hat Creek, in the shadow of Mount Lassen in Northern California, and it looks less like a research facility than like something abandoned. 42 white dishes, each about 6 meters across, standing in dry grass in irregular rows, all facing the same direction. It was funded in large part by Paul Allen, the co-founder of Microsoft, and it was built for one purpose that no other radio observatory in the world has ever been purpose-built for: to listen for someone. The institute that runs it has spent decades absorbing ridicule for that, and has responded by becoming extremely rigorous about what it will and will not claim. The team, led by Sophia Sheik, pointed the array at 3i/Atlas and listened for more than 7 hours, sweeping a wide range of frequencies and searching for a specific kind of signal: narrowband transmissions. This is the standard target of technosignature searches, and the reasoning behind it is sound. Nature broadcasts across wide swaths of the spectrum: thermal emission, synchrotron radiation, molecular lines that are broad because the molecules are moving. Nature is very bad at producing a signal concentrated into a razor-thin sliver of frequency. Technology, by contrast, does that constantly, because concentrating power into a narrowband is how you make a transmission efficient. Every radio station, every radar, every satellite downlink on Earth is narrowband. If a transmitter existed on that object, that is the shape its signal would most likely have. The first pass through the data flagged approximately 470,000 candidate signals. That number deserves a moment because it explains why this is hard. 470,000 narrowband hits in 7 hours from one small patch of sky. We live inside a fog of our own transmissions. Cell towers, aircraft transponders, satellite constellations, microwave ovens, badly shielded electronics in the observatory's own buildings. The sky as seen by a sensitive radio telescope is not quiet. It is deafening, and almost all of the noise is us. So SETI applies a filter that is simple and merciless. Point the telescope somewhere else. Any signal that persists when the dish is aimed away from the target cannot be coming from the target. It is local. It is interference. Run that test and the 470,000 collapse. Nothing survived. Not one candidate. The results were published in the Astronomical Journal in early June 2026, and the language was careful in the way that good null results are careful. No credible evidence of extraterrestrial technology was detected. And the paper's authors made a point that is easy to miss and that is arguably more interesting than the null itself. The sensitivity achieved was extraordinary. The search was capable of detecting transmitters at power levels comparable to a smartphone at that distance. A cell phone, if something on 3i/Atlas had been transmitting with the power of a handset in your pocket, on a narrowband frequency in the range swept during those 7 hours in the direction of Earth, it would have shown up. One of the researchers put it in the frame that matters most. The results demonstrate how realistic it now is to detect a signal with the technology we have today. That is the actual finding. Not that nobody was there, you cannot prove that, and no honest scientist claims to. But that we have built instruments capable of hearing a whisper across 100 million miles, and we now know how to use them on a target of opportunity, on short notice with the whole world watching. And the SETI Institute, an organization whose entire institutional interest lies in the possibility of detection, whose funding and reputation and reason for existing would be transformed overnight by a positive result, looked at the data and said, "It's a comet. That is worth pausing on." The most motivated party in the entire affair returned the least sensational answer available. Whatever else is broken about science as an institution, that particular mechanism worked exactly as designed. Which left the 16th of March. Picture the geometry, because it is genuinely beautiful and it is the last act of a passage that began before there was a Sunday Jupiter, 5 times farther from the Sun than Earth, a sphere so large that 11 Earths would span it and 1,300 would fill it, dragging its 95 known moons and its faint rings and its immense invisible magnetic field through the dark. And falling past it, from below and behind, moving retrograde against the grain of the entire solar system, a 5-kilometer body of ancient ice trailing a coma millions of kilometers wide, closing at 66 kilometers per second. Jupiter's speed and the comet's speed adding rather than subtracting, because they were moving in opposite directions. 53.5 million kilometers at closest approach. The wall of Jupiter's gravitational kingdom, passing through the boundary layer, close enough that Jupiter's pull would bend its path by a measurable amount and change, very slightly, the direction in which it would leave our solar system forever. Every large telescope on Earth was on it. Juno was in orbit at Jupiter. Juice was closing in from the inner system. Loeb had spent months telling people what to watch for, and the object did the single most eloquent thing available to it. It did nothing at all. No deceleration, no maneuver, no fragmentation into a swarm, no sudden change in brightness that could not be accounted for by geometry and outgassing. Nothing was released, and in the weeks and months that followed, as astronomers searched the space around Jupiter with the same instruments that have been steadily discovering small irregular moons for 2 decades, the 96th moon did not appear. Loeb himself, writing at the end of April, confirmed the position honestly. The fading light curve showed no evidence of artificial, self-produced light, and the community was still waiting on Juno's data. The test had been proposed. The test had been specified. The test had been run. Came back negative. By late April 2026, 3I/Atlas was 1 billion kilometers from the Sun, 6.7 astronomical units, out past Jupiter's orbit and climbing. Hubble caught it on the 10th of April as a fuzzy dot, and Loeb noted that it looked much the way it had when first spotted nearly a year earlier, except that now it was going the other way. Its outbound brightness was elevated relative to the same distance on the way in, which is exactly what you expect from a comet that shed a great deal of dust at perihelion and is now surrounded by a larger, more reflective cloud of debris. This path out is nearly symmetric to its path in. Nearly because the small non-gravitational acceleration from that remarkable system of jets tilted it slightly. It is heading toward the constellation Gemini at a radial velocity of about 58 kilometers per second. By the mid-2030s, it will cross the heliopause, the boundary where the sun's wind gives way to the wind between the stars. Following Voyager 1 and Voyager 2 out into a darkness they will all be crossing for millions of years. And then it will keep going, and the odds that it ever passes near another star closely enough to be seen are so small as to be a rounding error against eternity. We had it for 1 year, and where is it now? That question has a precise answer, and the answer keeps changing while you listen to this, which is part of what makes it strange. It is beyond Jupiter's orbit and climbing. It crossed 1 billion kilometers from the Sun in the spring of 2026, 6.7 astronomical units, and it has been adding roughly 5 million kilometers to that figure every day since. It is fading. Its coma is collapsing as the temperature drops back below the thresholds at which its various ices care about sunlight, and it is reverting layer by layer to the inert dark body it was for 10 billion years before we found it. Its outbound path is nearly a mirror of its inbound path. Nearly because the jets pushed it. A small non-gravitational acceleration, sustained over months, changed its velocity by a tiny amount and its direction by a tiny angle, and over interstellar distances a tiny angle becomes an enormous displacement. It will leave our solar system on a very slightly different heading than the one it would have had if it had passed a cold and silent Sunday. That difference, integrated over the next 10 billion years, amounts to hundreds of light years of divergence. Its exit heading is toward the constellation Gemini, with a radial velocity of about 58 kilometers per second. Gemini is a direction, not a destination. The stars we see there are between 18 and 2,000 light years away, in wildly different directions in 3 dimensions, and the object is not headed for any of them. Next, it must cross the outer solar system, Saturn's orbit, Uranus, Neptune at 30 astronomical units, which it will pass in a few years. Then the Kuiper Belt, the flattened donut of icy bodies where Pluto lives and where 100,000 objects larger than 100 kilometers are thought to reside. Then the scattered disk. And then, somewhere between 80 and 120 astronomical units, the heliopause. The heliopause is the real edge of the Sun's domain, and it is not defined by gravity. It is defined by wind. The sun continuously blows a stream of charged particles outward at hundreds of kilometers per second, and that solar wind carves a bubble in the interstellar medium, the heliosphere, and the heliopause is the surface where the outward pressure of our star's wind balances the pressure of the galactic medium pushing back. Cross it, and you are in interstellar space by the strictest definition, no longer inside anything the sun controls. Only 2 objects made by human hands have ever crossed it. Voyager 1 in 2012, Voyager 2 in 2018, both launched in 1977, both still faintly transmitting, both carrying a gold-plated copper record with greetings in 55 languages and a photograph of a mother nursing her child and Chuck Berry playing Johnny B. Good. They are the farthest things we have ever thrown. 3I/Atlas will cross the same boundary in the mid-2030s, moving more than 3 times faster than Voyager 1, and it will do it in the opposite sense, not leaving home but returning to it. For the Voyagers, the heliopause was the end of everything familiar. For 3I/Atlas, it is the far side of a brief and unprecedented interruption. Then the Oort cloud, and here the timescales stop being human at all. The Oort cloud is the outermost structure gravitationally attached to the Sun. A roughly spherical shell of icy bodies extending from a few thousand astronomical units out to perhaps 100,000, which is close to a light year and a half. It has never been directly observed. Its existence is inferred entirely from the orbits of long-period comets, which arrive from all directions with aphelia in that range, and the inference is solid. It is thought to contain trillions of objects, so sparsely distributed that a typical one is tens of millions of kilometers from its nearest neighbor. If you were standing on an Oort cloud body, the sun would be a bright star. Not a disk, a star among stars, distinguishable only by being slightly brighter than the rest. At 60 kilometers per second, crossing the Oort cloud takes on the order of 8,000 years. 8,000 years. Longer than recorded history. The object will pass through the outermost precinct of our solar system for a span of time that began, if we ran it backward, before the invention of writing, before the wheel, before agriculture had spread beyond a few river valleys. And during all 8,000 of those years, there will be nothing to see and nothing to encounter and no light to speak of. And then it will be out. Genuinely out. Between the stars at a few degrees above absolute zero, in a medium so thin it is functionally empty, and it will keep going. The sun, meanwhile, has about 5 billion years of hydrogen fusion left before it begins to fail. When that happens, it will swell into a red giant large enough to swallow Mercury and Venus and probably the Earth, and then it will shed its outer layers into a glowing shell that will disperse in a few tens of thousands of years, and what will remain is a white dwarf the size of our planet and the mass of a star, cooling slowly toward black. 3I/Atlas will be roughly 100,000 light-years away by then, which is to say it will have crossed the entire Milky Way and out the other side. And it will still be traveling. The universe is not going to stop it. There is nothing out there that will. It will drift for another 10 billion years, and another, past the point where star formation in the galaxy has essentially ceased for lack of fresh gas. Past the point where the Milky Way and Andromeda have collided and merged into a single formless elliptical, past the point where the accelerating expansion of the universe has carried every other galaxy out of view and left the local group alone in an empty and darkening sky. The ice will still be there. The organic crust will still be there. The deuterium ratio will still read out the temperature of a molecular cloud in a galaxy that existed 10 billion years before you were born. And for 1 year, in the 21st century of one calendar on one small planet, a species of primates with a talent for grinding glass and a stubborn refusal to leave anomalies alone caught it in the act of passing, and pointed everything they had at it, and argued furiously about what it was and found out. And here is where the story could end, tidily, with the skeptics vindicated and the anomaly hunters embarrassed, and that ending would be both accurate and almost entirely useless. Because the interesting question is not who was right. The interesting question is what the year actually produced, and the answer is a great deal more than a null result. Start with what we now know about the object itself, stripped of every argument about intent. 3I/Atlas is, by the current best analysis, the oldest object ever directly studied by human beings. 10 to 12 billion years old. It condensed out of a molecular cloud in a Milky Way that was young and violent and chemically poor, in an era astronomers call cosmic noon, when the universe was manufacturing stars at a rate it has never approached since and never will again. It froze at a temperature below 30 Kelvin, colder than anything in the modern solar system except the deepest shadows of the Kuiper belt. Its water carries 30 times more deuterium than ours. Its methane carries more still. It is chemically a message from a different galaxy, in the sense that the Milky Way of 10 billion years ago was, in every way that matters to chemistry, a different galaxy. Its velocity marks it as a member of the thick disk, the older, hotter, more scattered population of stars that orbits above and below the thin plane where the Sun and its neighbors live. It has been drifting for most of the age of the universe. It has crossed the galaxy's spiral arms more times than we can count, passed through star-forming regions, been gravitationally stirred by encounters it will never remember, and it has been in the dark and near absolute zero the entire time, until the 1st of July 2025, when a half-meter telescope in the Chilean desert caught it. We measured the water it was throwing off in real time from a spacecraft on the far side of the Sun that was never designed to do it. 2 tons a second. We traced its atmosphere out to 5 million kilometers. We photographed its jets and rays and filaments. We took its spectrum from the ultraviolet to the millimeter. We got a deuterium ratio, a carbon isotope ratio, a carbon dioxide to water ratio, a nickel abundance, a methanol abundance. We watched it brighten, turn blue, develop an anti-tail, accelerate, and fade. We built, in the space of a few months and largely out of improvisation, the most comprehensive characterization of an interstellar object in history, and we did it on something that gave us a one-time only window and no warning. And we did all of that because a great many people, for a great many different reasons, decided this one was worth dropping everything for. Some of them dropped everything because they thought it might be a spacecraft. Most of them did not. It does not matter. The instruments do not know why they were pointed, which is the argument for taking anomalies seriously that survives even after the anomaly evaporates. The scientific value of an aggressive response to a rare event does not depend on the exotic hypothesis being correct. It depends only on the event being rare and the window being short. And by that standard, the response to 3I/Atlas was, for all its institutional friction and its budget fights and its shutdown-induced silences, a substantial success. And the loudest advocate for that response was the man whose specific hypothesis turned out to be wrong. There is a version of intellectual honesty that consists of giving people credit for the parts they got right even when their headline claim collapsed, and the astronomical community has been uneven about extending it. It should, because the next one is coming, and soon. The Vera C. Rubin Observatory on a mountaintop in Chile not far from where Atlas found this one, carries the largest digital camera ever built for astronomy, 3.2 gigapixels, attached to a telescope designed to photograph the entire southern sky every few nights for 10 years. It is a machine built specifically to catch things that change and things that move. Estimates of how many interstellar objects it will detect vary widely, because our sample size is 3 and our error bars are enormous, but the numbers being discussed run from several per year to dozens. We are about to go from 3 known interstellar objects to a population with statistics, with a distribution, with the ability to say what is typical and what is genuinely strange. And when that happens, this year becomes the rehearsal. Every argument we had about 3I/Atlas, about how fast agencies can retarget spacecraft, about who pays for a mission extension, about whether images from a taxpayer-funded camera get released promptly, about what threshold of weirdness justifies a technosignature search, about how a scientist should communicate a low-probability hypothesis to a public that is not equipped to evaluate it. Every one of those arguments will be had again under time pressure with a new object. Better that we had them now, expensively and publicly and messily, on an object that turned out to be a comet. There is also a proposal on the table that would change the game entirely, and it grew directly out of the frustration of this passage. The core problem was that by the time we knew what 3I/Atlas was, it was too late to build anything to visit it. Interceptor concepts solve that by inverting the order of operations. You launch a spacecraft first, park it at a stable point in space, and let it wait, for years if necessary, until something comes through. Then you fire. ESA's Comet Interceptor, scheduled for launch in the late 2020s, is exactly this. A mission with no target, waiting in the dark for a target to appear. If it had been in position in 2025, the conversation about 3I/Atlas would have ended with photographs instead of arguments. That is the appropriate response to an anomaly. not certainty in either direction. Preparation. Which brings us to the question that will actually determine whether this year mattered. What do we do differently next time? The proposal that emerged from the wreckage of the 3i/Atlas observing campaign, and which Loeb himself co-authored in January 2026, is for a comprehensive network, an integrated system for the discovery and characterization of interstellar objects, designed from the ground up around the specific constraints these objects impose. Those constraints are brutal, and they are worth laying out, because they explain every frustration of the past year. First, the warning time is short. 3i/Atlas was discovered at 4.5 astronomical units, already inside Jupiter's orbit, 4 months from perihelion. That is actually a good case. Objects that are smaller, darker, or arriving from a direction closer to the Sun will be found later, or not at all. Our detection horizon for a body of this size is a few astronomical units, which at 60 kilometers per second is a matter of months. Second, the encounter is one time. There is no second pass, no orbit to wait for, no possibility of a follow-up mission a decade later. Whatever is not measured in the window is lost permanently. Third, the geometry is uncooperative. The object arrives from a random direction on a random trajectory, and there is no guarantee it will be well placed for observation from Earth. 3i/Atlas reached perihelion in solar conjunction. The next one might reach perihelion in a part of the sky only visible from the southern hemisphere in daylight. Fourth, spacecraft cannot be built on demand. A mission designed after discovery cannot possibly launch in time. The only way to have a spacecraft at an interstellar object is to have the spacecraft already flying. Every one of those constraints has an engineering answer, and every answer requires spending money before you know whether you will need it. The detection problem is being solved right now. The Vera C. Rubin Observatory in Chile began its 10-year legacy survey of space and time with a mirror system and a camera unlike anything previously built. A 3.2 gigapixel focal plane, images of 600 megabytes every 15 seconds, 20 terabytes of data per night, and an alert stream that will flag around 10 million changes in the sky every 24 hours. It will image the entire visible southern sky every 3 to 4 nights, to a depth that current surveys reach only with long dedicated exposures. Rubin was designed to find supernovae, map dark matter, and inventory the solar system, and interstellar objects fall out of that as a byproduct. Predictions of the yield vary from a few per year to several dozen, and the honest position is that nobody knows because our sample is 3. But the important thing about Rubin is not the count. It is the earliness. Rubin will find these objects farther out, which converts months of warning into years. The interception problem is being solved too, though more slowly. ESA's Comet Interceptor is scheduled to launch and park at the Sun-Earth L2 point, the same gravitational parking spot Webb uses, and simply wait. Carries no target. It is designed to sit in storage in space, potentially for years, until a suitable object is discovered, and then to depart and intercept. Its primary intended quarry is a pristine long-period comet from the Oort cloud on its first ever approach to the Sun, but an interstellar object would be an acceptable and spectacular alternative if the trajectory allowed. That is the correct architecture. Preposition the capability, then choose the target. It is the same logic that puts fire stations in neighborhoods before the fire. More ambitious proposals exist. Studies have looked at holding a small fleet of interceptors at various points in the solar system, at solar sail craft that could achieve very high velocities on short notice, at using nuclear electric propulsion to make rendezvous rather than flyby feasible. A rendezvous actually matching velocity actually flying alongside would be transformative, because it converts a few hours of flyby data into months of study and opens the possibility of a sample return. Getting a physical piece of a 10-billion-year-old interstellar object into a laboratory on Earth would be, without exaggeration, one of the most significant scientific achievements in human history. The isotopic and mineralogical analysis possible on a real sample dwarfs anything achievable remotely. The obstacle is speed. Matching 60 kilometers per second is beyond current propulsion. It is not beyond conceivable propulsion, and there are respectable engineering paths, and none of them will exist unless somebody starts building them a decade before they are needed. And there is one more piece of preparation that is not about hardware at all. If a genuinely ambiguous result ever does arrive, if some future object shows a signature that cannot be explained away and cannot be confirmed, the world will need a process that is agreed upon in advance. Not a secret one, public one, who verifies what thresholds count, how results are released and how fast and by whom. Post-detection protocols exist on paper, drafted by the international SETI community over decades, and they have never been stress-tested by an actual event with a global audience and a real-time information environment. The 3I/Atlas year was, in effect, a live drill, and the drill exposed exactly the weaknesses you would expect. Data releases delayed by budget politics. A vacuum filled by speculation faster than any institution could respond. A single loud voice able to set the terms of the public conversation because no institutional voice was willing to be interesting. Scientists talking to each other in a register the public reads as contempt. And a null result arriving 9 months after the exciting claim into an audience that had already moved on. Fix that and the next one goes better. Do not fix it and the next one goes worse because the next one will arrive into an information environment that is more fragmented and more automated than this one. None of which changes what actually happened at Jupiter on the 16th of March 2026, which was nothing, and which was exactly what a comet does. There is one more thing about the telescope that found it, and it closes a circle that runs through this entire story. Atlas was not built for discovery. Atlas was built for warning. It is a planetary defense instrument, funded by NASA's Planetary Defense Coordination Office, and its design specification was not elegance or depth. It was coverage. Scan everything every night or two as fast as possible, because the thing you are looking for might have a lead time measured in days. The numbers behind that mandate are not abstract. Roughly 100 tons of material falls onto the Earth every day, almost all of it dust. Every year, objects a few meters across enter the atmosphere and detonate at altitude with energies in the kiloton range, Hiroshima-scale explosions, distributed at random across a planet that is 70% ocean and mostly empty, which is why you have not heard about them. In February 2013, an object about 20 meters across entered over Chelyabinsk in Russia, exploded at an altitude of 30 kilometers with an energy around 30 times the Hiroshima yield, and injured roughly 1,500 people, almost all from flying glass when the shock wave arrived and blew out windows across 6 cities. Nobody saw it coming. It arrived from the direction of the sun, which is the blind spot no ground-based survey can cover. In 1908, something considerably larger detonated over the Podkamenia-Tunguska River in Siberia and flattened 80 million trees across 2,000 square kilometers. If that had happened 4 hours later, the same rotation of the Earth would have put St. Petersburg underneath it. And 66 million years ago, an object roughly 10 kilometers across, twice the largest estimate for the nucleus of 3I/Atlas, struck the shallow sea off what is now the Yucatan Peninsula, and the resulting event ended the Cretaceous, ended the non-avian dinosaurs, and cleared the ecological space in which mammals, and eventually we, expanded. That is the job Atlas was built to do. Find the next one early enough that somebody can do something about it. And in 2022, we demonstrated for the first time that somebody could. NASA's DART mission, the Double Asteroid Redirection Test, flew a 500-kilogram spacecraft into a small moon of the asteroid Didymos at 6 kilometers per second, deliberately on live video, and measurably changed its orbital period. It was the first time in the 4-billion-year history of this planet that life on it altered the trajectory of a celestial body on purpose. The change was small, which was the point. Applied years in advance, small is sufficient. We are, in other words, the first generation of Earth's inhabitants that is not entirely at the mercy of the sky. That capability is about a decade old. It is astonishingly cheap by any comparison you care to make, and it is chronically underfunded, and it exists because a relatively small number of people spent 30 years arguing that a low-probability, high-consequence risk deserved attention before rather than after. That argument, incidentally, is structurally identical to the one Loeb was making about interstellar objects. Take the improbable seriously enough to look. The difference is that the asteroid case eventually won on the merits, and that when it won, the instruments built to serve it turned out to be good for other things. Which is how a smoke alarm in the Chilean desert, scanning for the rock with our name on it, ended up making first physical contact with a fragment of the early universe. Nobody designed that. It is a byproduct. And the history of science is overwhelmingly a history of byproducts, of instruments built for one purpose returning something nobody anticipated, because the universe does not organize itself around our funding categories. Penzias and Wilson were trying to eliminate noise from a radio antenna and found the afterglow of the Big Bang. Fleming was careless with a petri dish. The Hubble Deep Field, a decision to point the world's most oversubscribed telescope at an empty patch of sky for 10 days, produced an image containing 3,000 galaxies where there had appeared to be nothing at all, and rewrote our estimate of how much universe there is. Build good instruments, point them at everything, and accept that most of what you find will not be what you were looking for. 3I/Atlas is the current best argument for that policy. A NASA-funded planetary defense survey, doing routine work on a routine night in the Chilean high desert, caught a moving dot. Within a year, that dot had been characterized by the James Webb Space Telescope, the Hubble Space Telescope, the Very Large Telescope, ALMA, SWIFT, SphereX, TESS, Subaru, a spacecraft in orbit at Jupiter, a spacecraft en route to Jupiter, a fleet of orbiters at Mars, a radio array in Northern California listening for transmitters, and several hundred amateur astronomers with backyard telescopes contributing positions that tightened the orbit. It turned out to be a 10-billion-year-old comet from a dead star in a younger galaxy, throwing 70 Olympic swimming pools of primordial water into space every day, and it grazed the outer wall of Jupiter's gravitational kingdom and left nothing behind. That is what happened. All of it is true, all of it is verifiable, and every part of it was more remarkable than the thing everyone was arguing about. Allow one final indulgence, because it is the question that was actually driving everything underneath the orbital mechanics and the isotope ratios and the arguments about probability. Not what happened. What if it had? Suppose that in the weeks after the 16th of March 2026, the survey teams that patiently count Jupiter's small outer moons had found one that was not there before. A 2-kilometer object in a bound retrograde orbit near the hill boundary. Confirmed by 3 independent groups on 3 continents. Orbit determined. Not there in the archival plates from January. What happens then? The first thing that happens is that nothing happens for a very long time, and this is the part almost no film about first contact gets right. There is no siren. There is no situation room. There is a period of months in which the finding is checked, rechecked, and attacked by everyone qualified to attack it, because the professional cost of a false positive on a claim of this magnitude is career-ending and everyone involved knows it. Archival searches would be run to exhaustion. Alternative explanations would be constructed. A previously undetected moon, a temporary capture of an ordinary asteroid, an error in the orbital solution. Each would be tested and, presumably, eliminated. That process takes a year, possibly 2. Meanwhile, the news leaks in week 1 because it always does, and the public conversation happens entirely without the verification. The second thing that happens is that the world discovers its protocols are theoretical. The international SETI community has drafted post-detection principles for decades. Verify before announcing, announce openly and internationally, do not respond on behalf of humanity without global consultation, and they are non-binding, unenforceable, and were written for a radio signal from a distant star, not for hardware in orbit around Jupiter with a 5-hour round-trip light time. There is no established authority. The United Nations Office for Outer Space Affairs exists and is not equipped for this. National security establishments would have their own views, and they would not be identical to the scientific community's views, and the resulting institutional conflict would be immediate and ugly. The third thing that happens is that the object is still there and we cannot get to it. Even a fully funded crash program to send a spacecraft to Jupiter takes 6 years minimum with existing propulsion. JUICE launched in 2023 and arrives in 2031. Whatever had been deposited would sit in orbit, being photographed from Earth as a point of light, unreachable for the better part of a decade, while the entire species argued about what to do. The fourth thing that happens is the part that should worry anyone who thinks about it honestly, and it is that we would have no idea whether it mattered. An object placed in orbit around Jupiter by something passing through 10 billion years after it was built might be an observation post. It might be a beacon. It might be a piece of debris from a mission whose purpose ended before the Earth formed. It might be dead. The overwhelming likelihood, given the timescales involved, is that whatever built it has been extinct for longer than complex life has existed on this planet. First contact with an artifact is not first contact with a civilization. It is archaeology at a distance we cannot travel, of a culture we cannot ask. And the fifth thing, the one that is genuinely unpredictable, is what it would do to us. Not to science. To everything else. Every religious tradition would have to metabolize it, and most would, because they have metabolized heliocentrism and deep time in evolution, and they are more flexible than their critics assume. Markets would react and then stop reacting. Governments would classify things. And after some interval, a year, 5 years, it would become ordinary because everything becomes ordinary, and the knowledge that we are not alone would take its place alongside the knowledge that the universe is 14 billion years old and mostly empty, which is to say it would be true and taught in schools and almost never thought about. That is the most likely outcome of the most dramatic event imaginable, and it tells you something about the durability of ordinary life. But none of that happened. No moon appeared. And here is the point of the exercise. The reason we can say that with confidence is that the question was asked properly. Somebody stated in advance, in public, with a date attached, what would count as evidence. That is a rare and valuable act, and it is rarer in this particular corner of human inquiry than almost anywhere else, because the field is saturated with claims constructed so that nothing could ever disconfirm them. Grainy footage, anonymous testimony, assertions that the absence of evidence is itself evidence of concealment. Against that background, a Harvard professor saying, here is the number, here is the date, here is what would prove me right, and then living with the result is an act of intellectual seriousness regardless of how it came out. The prediction failed. That is what a good prediction is allowed to do. That is the only thing that distinguishes it from a belief. And the object obliged us by being exactly what the boring answer said it was, which is the outcome that happens almost every time, and which is the reason the method works. But there is one more thread to pull, and it is the uncomfortable one, and any honest account has to include it because it is the part that will still be here long after 3i/Atlas has crossed the heliopause. Something happened to the public conversation during this year that was not really about astronomy at all. For roughly 12 months, a substantial slice of the internet was convinced that something was being concealed. Not by aliens, by NASA. The evidence for this belief was assembled from real materials. A mission extension that was not funded, a government shutdown that delayed image releases, a Harvard professor publicly complaining that he could not get answers about data from a camera at Mars, an object that reached its most dramatic moment while positioned exactly where Earth could not see it. Every one of those things was true, and arranged in sequence with the connective tissue supplied by the audience, they formed a story that felt airtight to millions of people. The actual explanations are so boring that they are almost impossible to convey. Mission extensions are decided by review panels working against fixed budgets, and Juno's extension request competed against every other extended mission in the portfolio, and $15 million is not free even when it is small. Government shutdowns halt public affairs offices, which is why images sat unreleased. JUICE's data took 3 months to arrive because the spacecraft was pointing its main antenna at the sun to keep from cooking, and had to phone home through a smaller one at a slower rate. Perihelion happened on the far side of the sun because orbits are geometry and geometry does not consult anyone's convenience. Not one of those explanations is satisfying. Every one of them is correct. And this is the structural problem that this story exposes more clearly than almost any recent episode. The truth in complex institutional systems is almost always less interesting than the narrative that fills the vacuum, and it arrives later, and it arrives in a form that requires background knowledge to evaluate. Speculation is fast, free, emotionally rewarding, and available instantly. Verification is slow, expensive, boring, and shows up 3 months later attached to a paper that most people will never read. In a competition between those two products, we should not be surprised which one wins. The remedy is not to stop speculating. The remedy is not to shame the curious, and it is certainly not to demand that people simply trust institutions. That request has been made too many times and honored too poorly. The remedy is the thing Loeb himself insisted on and then, in the eyes of his critics, failed to apply consistently to his own hypothesis. State in advance what would change your mind, then look, then honor the result. He did state it. 96th moon of Jupiter, after the 16th of March, 2026. No moon appeared. And the honest thing, the thing that separates a scientific claim from a belief, is to say the sentence out loud. The prediction was tested and it failed. That is not a humiliation. That is the entire mechanism. Every scientist who has ever contributed anything has stood in that position, and the ones we remember most fondly are frequently the ones who were spectacularly, productively wrong about something. Kelvin was wrong about the age of the Earth by a factor of 50, and it forced the discovery of radioactivity as a heat source. Hoyle was wrong about the Big Bang until he died, and along the way worked out how stars manufacture carbon, which is why you exist. Being wrong in public with a specific and testable claim is more valuable to the enterprise than being vaguely right in private, and it is infinitely more valuable than never committing to anything at all. So here is where we land. For 1 year, a piece of the early universe passed through our neighborhood, and we noticed. That is not a small thing. For the overwhelming majority of the time our species has existed, objects like this have been sliding past us constantly. The statistics suggest there is one inside the orbit of Neptune at essentially all times, and there have been billions of them since the Earth cooled, and we could not see them, and if we had seen them we could not have understood them, and if we had understood them we could have done nothing about it. In the 68 years between Sputnik and 3I/Atlas, we built the capacity to detect a 5-kilometer body arriving from another star, determine its trajectory to a fraction of a percent, measure the isotopic composition of its water from 400 million kilometers away, predict its closest approach to Jupiter 8 months in advance to within 400,000 kilometers, redirect a spacecraft's instruments on a few weeks' notice, and listen to it for narrowband radio signals at the power of a cell phone. 68 years. 2 human lifetimes, roughly. Your grandparents were alive for the beginning of it. We looked at an object that formed before the sun and asked whether anybody built it, and then we did the work to find out, and the answer was no. And the reason we can be reasonably confident the answer is no is not that anyone told us so. It is that a hypothesis was written down, a test was specified, instruments were pointed, and reality declined to cooperate. That is not a disappointment. That is the most reliable thing our species has ever built. And the thing itself, the actual object, the one that was hiding in plain sight the entire time behind the argument about what it might be, it deserves the last word because it is stranger than the story we told about it. It is a body of ice and dust and nickel and ancient organic chemistry, 5 kilometers across, assembled in the dark around a star whose name we will never know, in a galaxy still under construction, at a temperature 30 degrees above absolute zero, more than 10 billion years ago. It was thrown out of its home system by a gravitational encounter it did not survive to remember. It fell through the Milky Way for the entire subsequent history of the universe. During that fall, the sun ignited, the earth accreted, the oceans condensed. Life began and stayed single-celled for 3 billion years and then did not. Continents assembled and split. Ice ages came and went. A primate stood up on a savanna, and after a while it learned to knap flint, and then to farm, and then to write, and then to grind glass into lenses, and then to build a machine that could count the individual atoms of heavy hydrogen in a cloud of vapor 400 million kilometers away. And then, on the 1st of July 2025, the two histories intersected for 1 year. It came in from the direction of Sagittarius, from the heart of the galaxy. It swung around our star, and it threw 70 Olympic swimming pools of 10-billion-year-old water into space every day, water that had been frozen since before there was a sun to melt it. It passed the wall of Jupiter's gravitational kingdom on the 16th of March, 2026, and left nothing behind, and took nothing with it. And it is out there right now, the second, as you listen to this, a fading point falling toward Gemini at 58 kilometers per second, carrying its cargo of primordial ice back into the dark, where it will drift for another 10 billion years and another long after the sun has swollen and died and the earth has been erased and there is nobody left anywhere to point a telescope at anything. It was never hiding. We were just learning how to look. And the most extraordinary fact in this entire story, more extraordinary than any anomaly on any list, is that for 1 year on one small wet planet, a species that has existed for an eye blink managed to notice and understand and say goodbye.